regular meeting that we have in our community. It's happening every year. Last year it was in Brazil. It was also online. Hopefully next year it will be partially in person again. I would like to just give you a few reminders. So just the general form of the conference. So the first 2 days, we'll have 2 series of lectures by Olaf Hohm and Barton Zwiebach. Olaf will start the first lecture today, and it will be about L-infinity algebras, homotopy transfer, and field theory. Barton will take over from the second lecture today. On Wednesday, we'll start the research part of the conference. So we'll have about exactly 19 speakers. We'll have this 25 plus 5 minutes format. So we would like to ask you to avoid questions, or unless they're very urgent, in this 25 minutes, and then there will be 5 minutes left for questions at the end. And you should be aware also that there will be informal discussion sessions before the conference and after the conference starts every day. Yeah? On Friday, there will be a panel discussion with Ashok Sen, Nathan Berkowitz, Martin Schnabel, and Yuji Okawa. They're being very secretive about this because we haven't been communicating much, but hopefully it will be a great opportunity for us to look at the current state of SFT and its impact in physics in general. So it will have also this 30 plus 30 format, so 30 minutes for the panel and 30 minutes for open floor, so everybody can ask questions and discuss. On Wednesday, before the research part of the conference starts, we'll have this conference brunch. It will be held in Gathertown, so you might want to get acquainted with it, but it's a very nice, very informal. Of course, food will not be provided. And just some general information. So we have several interaction channels, mainly Zoom, because that's where the conference will be broadcast. We have also Zulip for offline chat, and you can ask questions there every time you want. And then Gathertown, that's the one for Wednesday. In all these interactions, please use your real name so we can identify ourselves and be a bit more informal. And please follow these guidelines. Maintain civility at all times in our discourses for the meeting, verbal or written. Yes? We'll try to be very strict about this. So please keep this in mind. And let me just here, just another reminder, we have this email for the conference. So if you have any problems connecting or accessing some content online in the website or problems with the Zulip chat, please do not avoid contacting us. Another few reminders for the speakers and lecturers. It would be very nice to have your slides before the talks and lecture notes after, as you please. But especially for people with not very good internet connection, it would be nice to have the slides for the research talks beforehand. During the Zoom meeting, please keep your microphone and camera off unless you're asking questions. Further links will be sent for Gathertown and maybe specific Zulip channels for the interactions. And again, please contact us if you have any problem or, well, any comments and so on. So we'll start today's section with Olaf Hohm, and he will talk about L-infinity algebras and their connection to field theories. Please, welcome, Olaf.
Okay, thank you very much. Let me share my screen. Okay, can you all see my screen?
Yes, it seems to be working well.
Okay, thank you very much for the opportunity to present this material here. So I'm honored and humbled to introduce L-infinity algebras, homotopy transfer, and field theory to this audience. So many of you I know are experts on this subject. In fact, some of you have developed the key technical aspects here. So I'm sort of in the funny situation to introduce material that most of you or many of you know already. But my understanding is that this is, I here see a comment that there's an echo. Okay, this may be due to my, I hear that too. So let me try the following. I will log out from, I logged in through 2 accounts. I will log out from this one and will only use my iPad. So let's try, let's see if that works. Can you hear me?
Yes.
Yes. Okay. Let's go back here. Do you still see the slides?
No, it's fine. The sound is good.
The sound is better? Okay. So, all right. So as I said, I'm very honored and humbled to give this lecture. This is a lecture in 3 parts. So the first lecture today will be just introducing L-infinity algebras. So it will be mostly mathematical. Then the second and third part of the title and the lecture series are homotopy transfer and field theory. So the second part will be on field theory and the last part on homotopy transfer. Here it's written the other way around because it was swapped in the schedule at some point and I wanted to make a joke, but now it's corrected. So anyway, so this is mainly based on 3 papers I've written. The first one was with Barton Zwiebach in 2017, and then 2 more recent papers, one last year, one this year, with Alex Avanitakis, who will also speak at this conference later this week, with Chris Hull and with Victor Lequeux, where we mainly work out homotopy transfer and the field theory applications. So as I started to say earlier, this material will be familiar to many in the audience, but my understanding is that this is supposed to be understandable for a broader audience and that there will be many students and people with not so much experience in the audience. And so this is really meant for them. In particular, I will try to be as pedagogical as possible so we can keep this rather informal. So whenever you have a question, please interrupt me, just speak up, because otherwise if I may not see it. And we can discuss. And yeah, well, let's just start. So as I said, today will be largely mathematical, so an introduction into L-infinity algebras. But before going through that, let me give you the motivation or the big picture, where I'm heading at with this. And I want to illustrate this main idea with the example of Young-Mills theory, just something that's familiar to everyone. So in Young-Mills theory, of course, we have a basic field, which is the one form A mu, which is a field that takes values on the Lie algebra. So you can take here the basic field and expand it into a basis of generators. That's the expansion here. So A mu takes values in the Lie algebra. Then there's a 0 form, of course, which is the gauge parameter lambda, which generates or defines the gauge transformation as given here. And then I have a 2 form, which is the curvature, the field strength, which is written here. And just to make something very simple, completely explicit, this notation here for the commutator a comma a, of course, just means that this is a two-form defined in components by the commutator, by the Lie bracket a mu is a nu times the differentials dx mu wedge dx nu. Now, the point I want to make here is that in this standard construction of Yang-Mills theory, I have what is called the differential graded Lie algebra. A differential graded Lie algebra is a vector space equipped with a differential and a graded Lie bracket. So let me give you the formal definition, and then we can immediately check that the standard construction of Yang-Mills theory is a particular example of a differential graded Lie algebra. So we start with what is called the chain complex. That's just a vector space X. So that's a graded vector space, which means that it decomposes into subspaces x1, x2, x3, and perhaps also negative degree ones, and differential D. And so I have a sequence of vector spaces as written here, x0, x1, x2, and I have this differential map, which maps between x0 and x1, x1 and x2, etc. So I can, to make this explicit, also indicate this with a sub-index 0, 1, 2, etc. And this differential squares to 0. D squared is equal to 0. And more precisely, I should state this as the composition of maps like D1 with D0 gives 0, D2 with D1 gives 0, etc. So in the example we had, you can just think of these vector spaces of the spaces of 0 forms, 1 form, 2 forms, and the D is just the ordinary de Rham differential. So I have the chain complex, and the second ingredient is the graded antisymmetric Lie bracket. So that's an antisymmetric bilinear operation, indicated by these brackets here, which is graded antisymmetric. So that means I have this exchange property. And in some conventions, I can make a statement about the degree of the outcome if I have two inputs, x1 and x2, which is this equation here. So in the example of the forms, just means that if I take the brackets of two one forms, let's say I get a two form, etc., etc. Okay, so that is needed in particular in order to make the simple statement that if I have two elements of x1, the space of one forms, then the bracket on these one forms is actually symmetric, as given here. So that due to the graded antisymmetry, can happen that the bracket is actually symmetric or antisymmetric, which in this case it is symmetric. And that's, of course, as needed in order to write this term. So I'm just making a simple point here explicit that sometimes causes confusion for beginners, which is that if you see the bracket A with A, you think that should be 0 because the bracket is antisymmetric. But of course, it's the grading that really saves the situation. So these are the basic structures. And now we have three axioms that should be obeyed. The first one we stated already, which is d squared equal to 0. The second one is the Leibniz relation, which gives a relation between the differential and the bracket. So if I act with the d on a bracket evaluated in x and y some generic elements of the space, then I should be able to move the differential inside according to the Leibniz rule with a sign that depends on the sign of the argument x over which the d had to jump, so to say. And then there is a nested relation, which is the graded Jacobi identity. So that's the third relation here. And that's just the graded version of the familiar Jacobi identity. Okay, so if you start from an ordinary Lie algebra, as we do in Yang-Mills theory, and you, so to say, tensor it with the differential forms, you introduce 0 forms, 1 forms, 2 forms, etc., that each take values in the Lie algebra, then you have actually defined a differential graded Lie algebra, fulfilling these axioms here. So you have an antisymmetric bracket you have a differential, which is just the usual de Rham differential, and these relations here are obeyed. And in particular, although the original Lie bracket that defines Young-Mills theory is of course an ordinary Lie bracket without a grading, this bigger algebra where you have the p-forms introduced has a grading as is needed in order to define meaningful curvatures, etc. Okay, so that's of course the basic structure that we need, for instance, in order to define Chern-Simons theory in 2 + 1 dimensions. Chern-Simons theory in 2 + 1 dimensions is a particular instance of a Young-Mills gauge theory. And it's a particularly nice one because it really only uses these basic structures of the differential graded Lie algebra. More precisely, in order to write an action, as we've done here, in order to write this action, I also need an inner product that is invariant. But if I have that, I can write the action, and the equations of motion are then just the statement that the field strength is 0, and these field strengths expression that I have here only uses the structures of the differential graded Lie algebra. So it uses the differential and it uses the 2 bracket, the Lie bracket, and nothing else. And this equation is also called the Morrow-Cartan equation. So this theory, of course, we like very much. It's Chern-Simons theory in 2 + 1 dimensions because it has this simple structure. But of course, it's very special. It's a topological field theory. It is very degenerate. It's not related to any of the more realistic theories we like. But it turns out that if one relaxes the axioms of a DGLA a little bit, one can actually encompass any possible classical field theory in this framework. And this is the main message that I want to get across before I get started on the formal developments, which is that any classical field theory can be encoded in the structures of what's called an L-infinity algebra, which is a generalization of the differential graded Lie algebra. So it's basically a structure like this basic differential graded Lie algebra we all are familiar with from Young-Mills theory. But you have to do 2 things. First, you have to abstract the notions of differential and bracket. So the differential is no longer just the de Rham differential, at least not in general. And the bracket need not come from an ordinary Lie bracket by just tensoring with some simple objects. But the basic axioms will be the same, except, and this is now the second generalization, that we need higher brackets in the game. So the equations of motion, for instance, can always be written, that's the claim, as a generalized Morrow-Cartan type equation, which is written down here, which looks exactly like the equation we had before, except that now the differential, which I call partial in order to distinguish it from the de Rham differential, may be a different object, but it still needs to square to 0. And then I may need higher brackets, like a 3 bracket, a 4 bracket, and in fact, generically an infinite number of brackets, as happens, for instance, in gravity or closed string field theory. But the basic axioms of the DGLA will have to be generalized to the axioms of an L-infinity algebra, and then any classical field theory can be encoded as an L-infinity algebra. So that's the main message I wanted to briefly summarize before I get started on the more purely mathematical part for the first lecture of how to define explicitly an L-infinity algebra. So any questions on this general introduction before I come to L-infinity? Okay, if not, then let me get started. So this is for today, the introduction to L-infinity algebras. Just before I get started, a brief comment to get something very general out of the way, which is that L-infinity algebras are closely related to the classical limit of the Batalin-Bilkovitsky or BV formalism. In fact, whenever you have a BV structure, you also have an associated L-infinity algebra. So the two are very closely connected, and that often leads to questions and discussions why one distinguishes the two notions. But it's important to recognize that L-infinity algebras have sort of an independent existence. In particular, they have generally less structure, and you don't need extra fields and various other ingredients. And in the particular way I want to introduce L-infinity algebras in these lectures, there's also a conceptual difference that for certain viewpoints are more convenient. In particular, BV structure is naturally formulated in terms of a vector field on a supermanifold, an odd or nilpotent vector field on a supermanifold, which is therefore a derivation because it's a vector field. What I will introduce today is the L-infinity algebra formulation in terms of co-derivations. So it's two kind of very closely related, but conceptually slightly different viewpoints. One is a co-algebra versus an algebra, or a co-derivation versus a derivation. So that just as a general comment to point this out. And now let's get started with the definition. So this is not yet the complete definition. There are various ingredients that I have to define along the way, but I want to give you the bigger picture to begin with. So exactly in the same way as we have seen it for a differential graded Lie algebra, an L-infinity algebra is a vector space, more precisely a graded vector space. So that means I can write X as a direct sum of xi's, where I runs over the integers. So I have an integer graded vector space. And this vector space is equipped with multilinear graded symmetric brackets that in turn satisfy certain generalized Jacobi identities. So the notation I will use here is the usual square brackets. So I have brackets for any number of inputs x1 to xn. So n can run from 1 to infinity. So in particular, I have a 1 bracket, which just means I have a map from the vector space to itself. That is the B1. And then, of course, I have all kinds of higher brackets. I have the B2, which is just the 2 bracket that also the differential graded Lie algebra had. And then I have a 3 bracket, a 4 bracket, etc. And these brackets have a fixed intrinsic degree, which means that the outcome of this operation, so if I apply the square brackets or the Bn notation that I use here, and I plug in n vectors x1 to xn, the outcome lives in the vector space with a particular integer degree, which is just the sum of all the arguments degrees minus 1, as indicated here. So this is sometimes summarized by saying that's the intrinsic degree of the Bn's is minus 1. So that means that the outcome, the degree of the outcome is the sum of the degrees of the arguments minus 1. So this is a particular convention I'm using here. It's called the B-picture convention, in which the brackets are graded symmetric as opposed to graded antisymmetric. And so that's already different from the basic DGLA axioms I gave you before, the differential graded Lie algebra axioms, where it's more convenient to use graded antisymmetry. But you can actually convince yourselves with a few examples that that's just a change of convention. So if you shift the degree of the vector spaces and introduce some signs in the definition of the brackets, you can go from one to the other. So what I will use here is the B-picture convention where the Bn's are graded symmetric. So that means whenever I exchange 2 arguments, I don't get a sign unless both arguments are odd, in which case I get a sign. Okay. So as I already emphasized, I will use these 2 notations for the basic brackets of the L-infinity algebra. I will use the Bn's, where n runs from 1 to infinity. So I have B1, B2. But I sometimes will also denote the B1 by this symbol partial to remind ourselves that this is the differential. And then I will also use this bracket notation, like for B2 and for higher brackets. And so all that is left, and that unfortunately will take us a little time to finalize, all that is left to actually write down what the Jacobi identities are. And we will use the formulation in terms of co-derivations, where the Jacobi identities are just the statement that there's a certain derivation operator D, which is the sum of all the B's, squares to 0. And then the statement that D squared is 0 encodes the generalized Jacobi identities. The work that is left to do here is to make this definition, first of all, meaningful, because as written, of course, it's nonsense, because the B1 is an object that takes one input, the B2 is an object that takes two inputs, etc., etc. So it doesn't make sense to add them up. It's like adding apples and pears. So as written, this is not a meaningful statement, but you can make this into a meaningful statement by upgrading this, well, defining this D as a so-called co-derivation on a larger vector space, which is the graded symmetric tensor co-algebra. I'm not sure if that's the right name, but something like this. So we'll go over to a larger vector space now that consists not only of the original vector space, but also of all higher tensor powers of this basic space. And I will explain what this means. And the point is that on this larger space, we have an action on all these BNs. So all these BNs can now be viewed as maps on the same space. And hence it makes sense to add them up and to take the square. That's also a non-trivial statement that you can do that. And then this is just the definition of the L-infinity algebra. Okay. Any questions so far? Maybe someone just can give me feedback that you're still around, because now I can't see anymore.
Sorry, no, we're still around. Perfect.
Okay, good. All right. So as I said, we will have to go over to this larger vector space in order to define this co-derivation.
Just one second, there is someone who raised their hand.
Yes, please.
Rito?
Yeah, earlier when you said that any classical field theory can be encoded in the L-infinity algebras. So once we write it in terms of the L-infinity variables, for evaluating correlation function, do we use the same technique as the Feynman rules, how we do like in ordinary case? Or is there?
Yes. So first, as I said, it's a statement of the classical theory. So you can talk about tree-level scattering amplitudes, and there's indeed a nice story how to relate operate natural operations in L-infinity algebras to Feynman rules. So we may come to that, but that's true. Yeah. Did this answer your question? We will probably have more time to discuss that tomorrow. Any other questions? Okay, if not, let me continue. So as I said, we want to define this larger vector space on which the co-derivation, that is just the sum of all the L-infinity maps, can be defined, and that's a graded symmetric tensor algebra. And that's the object here. So very formally define it like this. And that just means, that's just fancy notation for saying that this is a sum of vector spaces that consists of the original vector space, which I call S1X here. It's the original vector space, capital X. But then you take all higher graded symmetric tensor powers, by which I mean that you have a space like S2X, which consists of elements X1 wedge X2. So we have now this new notation, which defines the elements of S2X. So if I have two vectors in the original vector space, X1 and X2, I use this wedge notation to build a new vector. So it's basically just like a tensor product, except that it's graded symmetric. So it's not just the general x1 tensor x2. It's graded symmetric, which means that this is supposed to be equal to x2 wedge x1 up to a sign that depends on the degrees of x1 and x2. So if both are odd, then there's a sign, otherwise there's no sign. And this pattern continues. I also allow objects x1, wedge x2, wedge x3, etc. So this, in general, the space SNX consists of an n-fold symmetric tensor power x1 wedge to wedge xn, and that's supposed to be the same vector. This equal to any vector obtained by any reshuffling of the permutations of the arguments. So in other words, if I consider any permutation sigma, then this is equal to x sigma of 1 wedge x sigma of n up to a sign, and the sign is just the sign obtained by permuting the elements according to this basic rule I had up here. And this sign has a name, it's the Koszul sign associated to this permutation sigma, and also depends on the objects I'm permuting. Because if the objects are all even or all odd or some mixture, of course, that affects the final sign I get. Okay, so that's the vector space. If you're not familiar with this kind of thing, it's rather abstract, but I mean, at the end of the day, it's rather concrete because the elements are just all formal sums of vectors of this obtained from the basic vector space X by taking various wedge products subject to these anti-symmetry properties. Okay, so that's the vector space. Now on this vector space, we have a certain structure. In fact, we have several structures. We also have an algebra structure, but that's not the one I'm interested in. The relevant one for us is a sort of co-algebra structure. So a co-algebra structure means that you don't have a product as you would have for an algebra, but you rather have a co-product. So a co-product is a map from the vector space S, in this case, into S tensor S. So that means you take one vector and you get as an outcome two vectors. So something in S tensor S, which is the opposite of what a normal product does. Okay, so that takes some time getting used to, but it exists here, and it works as follows. So this co-product basically takes any tensor power graded symmetric of this big vector space S. So just as a reminder, this S is just this space I have up here. It takes a vector in that bigger space, and it decomposes it in all possible ways. So if I have a single vector X, an element of the original space capital X, then delta X equals 0. Not so interesting. So the first interesting case is the one here, where I consider X1 wedge X2. So that's an element of S2 of X. And I want to make out of this an element of S tensor S. So basically I want to take this one object and make two out of it. And how can I do this? Well, it's sort of obvious here. You take out X1 and X2 and build X1 tensor X2. Very simple. The only thing you have to remember is that this is supposed to be graded symmetric. So you have to do this decomposition in a way that respects the graded symmetry. And that you simply do by symmetrizing the result. So the outcome here is X1 tensor X2 plus minus X2 tensor X1, where the sign again depends on the sign of the two vectors. And similarly,
may I ask a question?
Yes, please.
You are essentially defining the co-algebra action on a basis and then extending its action to the whole S by linearity, I guess.
Yes, that's right.
Okay.
I mean, it's not necessarily a basis here because the X, well,
yes, it's a kind of a pure state, let us say this way.
Yeah, right. That's probably a good analogy. Okay, so then we have the co-product on x1, wedge x2, wedge x3. So again, you take all possible ways to take this apart. So you can, for instance, take out the x1 and then leave x2, wedge x3 as it is. And of course, again, there are 3 ways up to symmetry of doing that, and you have to symmetrize in all of them. So we get 3 terms for taking out x1, x2, or x3, and the signs are sort of the obvious one obtained by changing the order of the original object. And then, yes.
Hello.
Yeah.
I have a question.
Yes.
Like the x1, x2, etc. are elements of the original vector space
Yes,
capital
that's
X, right?
Yeah.
So what does it mean when we take -1 to the power x1, x2? Like what's
Yes.
what's that?
Yes, thanks for the question. So I should have explained that. That is just notation for, so I just use this notation. That's just the degree. So if I denote by every vector has a degree, and that's just a number, right? It's the integer associated to the vector, and that's what I mean by this notation. So this notation just indicates the sign that I get by permuting x1, x2, etc.
Okay. What do you mean by degree of?
Degree
that
means,
vector?
yeah, I replace one notation by another, right? Without explaining. So I have this decomposition here, right? And so if I have an x, so if I have a vector x in capital X, and let's say it's an element of xi, okay? So this, I mean, of course, since it's a direct sum, I can also take direct sums. I can also take formal sums of vectors in x1 and x2, in which case this is not what one would call a homogeneous element, and then there is no well-defined degree. But let's say I have an x in xi, then I is simply the degree. So then degree of x is just the I.
Okay.
So of course, what matters in all these formulas is not the actual number, but just whether it's even or odd, because that determines the sign. Did this clarify the notation?
Yeah. Thank you.
Okay. Any other questions?
I have another question.
Yes.
Yes. So why is the identity element kind of not existing in your co-algebra? Is there significance to that? Or I don't know how to say it, but like
you mean why I'm not saying delta of x is 1 or something like this? Or
delta of x equals, well, actually, I'm thinking even earlier, your sum that's defining the symmetrized co-algebra goes from n equals 1 to infinity rather than n equals 0. I'm wondering what happened to the n equals 0, or if that's significant.
Yeah. Well, I'm not sure if I can give you a very good answer straight away. So this is the construction that works, and for the particular applications I have in mind. Now, this may not be the most general one that people consider in this context. So,
okay.
I may have to think about this, whether I can give you a better answer. It's just that that's the particular procedure I use for now. And unless I made a mistake, it seems to work. But maybe there should be a better answer. But
it's just a little different from what I'm familiar with. But
yeah, I guess in many contexts one does it slightly differently.
Okay.
But let's go on. Maybe we'll see if there's a deeper significance to it, but maybe not. Okay. So this was just the co-product on 2 examples, but there's also a general formula which is given here, And so the basic rule is just what we've seen, for example. So you have this monomial x1 wedge to xn, and we basically split it up in two subsets, and we sum over all possible ways of doing that. But we leave the order of each subset intact. So that means I have here two factors, x sigma 1 to x sigma I, and x sigma I plus 1 to x sigma n, where sigma is a permutation. So I sum over all permutations, but not actually over all permutations, but only over permutations that satisfy this relation here. So that means that the order of these two subsets, one going from 1 to I and one going from I plus 1 to n, is left intact. And those permutations have a name. They're called unshuffles. So that can be related to the shuffling of a deck of cards. I won't do this here. It's just the name I use for now. And the sign that is obtained here is the sign that you obtain by reordering the arguments, and that's the Koschel sign I defined up here. But the basic three examples should give you sort of a feeling of how this actually works. Okay. So this is the co-product. Just give me a second. So this was the definition of the co-product on this large vector space S. And this co-product has an important property, which is called that co-associative. So it's co-associative. And that is sort of the dual of the statement that a product is associative. And as often in this business, one can express that as a statement that a certain diagram is commutative. So if you start from S, you can take the co-product and go to S tensor S, as we just seen. And then you can act again with the co-product, and you can decide whether you act on the second S or the first S. So you can write this as either acting with one tensor delta or with delta tensor 1, and then you get something in S tensor S tensor S. And for this to be co-associative, you want that this commutes. And that the claim is that this is indeed the case for the co-product I defined above. It satisfies this relation here, which I can also write explicitly as a formula in this boxed equation. And just to relate it to this more familiar property of associativity of a product, suppose I have a product M on a vector space S, then I can think of it as a map from S tensor S into S. And there the associativity means this equation given down here. So in other words, if I first act with the multiplication on the two leftmost factors, and then a multiplication on the result, that should be the same as if I first act on the other two factors, so M tensor 1, and then I act with M. So this notation may look a little unfamiliar, but if you write it out as a map on S tensor S, explicitly, you see that that's just normal associativity. And the boxed equation here is sort of the dual version of that. And dual just means that all the maps go in the other direction. So that's the familiar fact that if you have a map from a vector space X into another vector space Y, then the dual map goes in the other direction from Y star to X star, and all the maps sort of swap around. So in that sense, that is indeed properly called co-associativity. Okay, now from, I mean, it's of course not obvious that this co-product satisfies this property, but you can check, for instance, with these formulas here. It's a nice exercise to check this for a few examples to see that this is indeed a co-associative co-algebra. Okay, so this was a lot of preparation for the basic definition. we are really after, which is that of a co-derivation. So a co-derivation is a map, D, capital D, as written here, from S into S, which obeys the co-Leibniz property with respect to the co-product. And the co-Leibniz property is written here. So it's a relation between the co-product and the co-derivation. So here it's just written as an equation. You can again re-express that as a certain diagram commuting, but it's also clear that this is the proper definition that is the dual to the statement that a derivation obeys the Leibniz property with respect to a product M. So if you had a product M as before, then we would express the Leibniz property as follows. So if you have, you act with M first on two elements, and then you act with the D, you can move the D inside according to the Leibniz rule. So that means the effect is the same as acting with 1 tensor D plus D tensor 1, and then acting with M afterwards. And so the corresponding equation for the co-derivation is in the box version above. It's just the dual statement again, where you swap all symbols. So every map goes to a dual map. And so that makes sense. Then because the co-derivation is the dual to a derivation, and the co-product is the dual to a product. So that's the co-Leibniz property. And now we have everything we need to give the real definition, the complete definition of an L-infinity algebra, which is that an L-infinity algebra is a Z-graded vector space capital X that comes with a structure, and that structure is the co-derivation D, which consists of the sum of co-derivations Bi, so it's B1 plus B2 plus B2, and everything has degree, intrinsic degree -1. That's a choice of convention here. We could also call it +1. So this D is a co-derivation of degree -1, and that squares to 0. D squared is 0. So maybe something one should have added here is that if D is a co-derivation of degree -1, or if D is an odd degree co-derivation, then D squared is also a co-derivation. And it's equal to 0. So that's the definition. Now, the rest of today's lecture, I just want to write out what that means explicitly in terms of the maps, and to make this more concrete. So for this, let's just work out a few examples and get some intuition of what that means. So I want to understand with a few examples what the action of the BI is. So let's start with B1, and let's suppose I act on a single vector X of the original vector space. Well, here I don't really have to explain anything, because B1 starts its life basically as a map on the vector space X. So given a vector X, I know what to do. I'm supposed to know what to do when acting with B1. So there's nothing to explain. Now, what is B2 on X? Or B3 on X, where X is still just a single vector from the underlying vector space? Well, that's the only thing I can do with it. I can really set it to 0. Not much else I can do. So the next interesting case is this one here. Suppose now I act with B1 on an element of the space S2X. So it consists of quadratic expressions, X wedge Y. Well, you might have guessed it, but you can actually also prove it using the definitions above, that the B1 just acts by this Leibniz rule according to this formula. So you first act on X, B1 X wedge Y, and then you act on Y. And since you had to jump over X, there might be a sign -1 to the X. So the B1 part actually also acts like a derivation. This is a co-derivation, but for this special case, it looks exactly like for a derivation. So you have just the normal Leibniz rule. And it's a nice exercise to check that this is exactly as it should be in order to obey this basic relation here. So that, just as a reminder, this was the co-Leibniz property co-derivation. So, I mean, that's what defines the co-derivation, that it satisfies this relation here. And you can check that with this definition, this Leibniz-like formula is correct. Okay, so that's exactly as you would expect. Now, how does B2 act? Well, on X wedge Y, which is the case here, again, there's nothing really to explain because that's how B2 started its life, as a map that acts on two elements, X and Y, and gives you a vector of this underlying vector space. And everything is graded symmetric, so everything is compatible. There's no ambiguity. And B2 of X comma Y is also written in this bracket notation. So the next interesting case is this one here. Suppose now you act with B2 on a third order monomial, X1 wedge X2 wedge X3. So this is now the case where it becomes interesting, where it's not so obvious what to do anymore, and where the definition in terms of co-derivations gives you a rule of what to do. So it's sort of, I mean, the philosophy is really exactly like for derivations and algebras. So if you have an algebra and a derivation, you really only need to know how the different derivation acts on a single element, because if you have the Leibniz property, you can always work out how it acts on higher powers. So if you have, abstractly speaking, a derivation D and a multiplication that allows you to build XY, then you also know how dx on xy, which is just by the Leibniz rule. And basically, we have the same kind of machinery available for co-algebras and co-derivations. And this is illustrated here. So if you know how B2 acts on two elements, like here, you also can work out how it acts on higher elements. The specific formula looks something like this. And it's, again, if you think about it, sort of the only thing you could do. So you have the B2 acting on X1, wedge X2, wedge X3. So what you can do is you can pick out two of the three elements, you let B2 act on it to produce a vector, and then you wedge it with the final vector, in this case, here X3, that you didn't act on. So that's a valid operation. Of course, it's by itself that wouldn't work because it singles out X1 and X2 compared to X3, and the result is supposed to be graded symmetric in 1, 2, and 3. And so what you do is just symmetrize in all three permutations. So, for instance, if the second term here is obtained by moving X2 and X3 to the front, keeping the signs obtained by doing so, then acting with B2. So you act with B2 and X2 and X3, and then you wedge with X1. And the sign here is just the sign that you would get if you move X2 and X3 to the front. So you have you move X2 past X1, that gives you the X2, X1, and then you move the X3 past X1, that gives you the X3, X1. And similarly, the final term, if you move 3 and 1 to the front, you get this term here. And again, the sign is the one obtained by moving X3 past X1 and X2, so that it's in front, and then you act as B2. So that is basically, in words, I think, close to the best explanation you can give, more illuminating than these formulas usually are. You act with a B on a certain monomial that has, so if you have a Bn, you act on a monomial of degree n. That's just the basic definition. If the degree is less than n, it's 0. If it's larger than n, you have to use this rule where you add on a subset of the vectors, but you have to sum over all possibilities of doing that, taking out sort of trivial permutations. So here, for instance, in the first term, you have only one term. You don't bother symmetrizing over X1 and X2 because B2 is already graded symmetric in 1 and 2 in its two arguments. So that means you're not summing over all permutations, but only over the subset of permutations which are introduced above, which are called the unshuffles. So here's the fancy formula that should summarize what I just said in words. So you extend the BIs to maps on this big vector space. So on an object in SJX, where J is equal to I or larger than I, otherwise it's trivial, you have an extension of the map BI that maps it into Sj minus I plus 1 X, which just means that you take out I of these J vectors, you let B act on it and produce another vector, because that's what B does. So that's why the degree here comes out to be J minus I plus 1, because you first take out I and then you act with B to produce another one. And the formula is as given here. You sum over all permutations that are unshuffled according to the definition above, which with the examples should be clear what that means. And you produce, of course, the signs of the encoded in the Koschel sign, which is just a fancy way of saying that it's just the signs obtained by moving these vectors around. Okay, so let's work it out for the first few relations. So the definition of an L-infinity algebra was that D squared is equal to 0 for capital D being equal to B1 plus B2 plus B3. So if you square this, you get an infinite number of relations of this kind. So first of all, you get B1 squared is 0. That's just the leading term. And of course, that we knew already. So B1 is just the differential, so that should square to 0. Then you get B1, B2 plus B2, B1 equal to 0. It's the second one. And the third one, you get B2 squared plus B1, B3 plus B3, B1 equal to 0. And you can imagine that this just continues naturally indefinitely. Okay, so as I just said, the first relation we know already. That just tells me that B1 is a differential, which I also denote by partial, which is nilpotent, so it squares to 0. The second one now gets a little more interesting. You can actually work out or see what the co-derivations do in practice. So the statement is that B1, B2 plus B2, B1 is 0 acting on anything in this big vector space. So in particular, I can let it act on x1 wedge x2. Okay, so for the first one, the first term here, that's easy. The B2 acting on x1 wedge x2 is just, well, as we said, it's just B2 evaluated on x1, x2, and then I act with B1 after that. So this term is what you expect. The second term here, however, that produces two terms for the simple reason that now I have to use this co-derivation rule to let B1 act on x1 wedge x2. And again, this is something that we have seen how to do, which is this boxed equation here. The B1 actually just acts like a normal derivation. So here the Leibniz rule just looks like the normal Leibniz rule, and that's what produces this term here. Okay, so that's just that's now the L-infinity relation number 2, and you can see that this looks exactly like the Leibniz property of a differential graded Lie algebra that I had at the very beginning. So I had the differential B1 or partial and the 2 bracket B2, or just the bracket, and that was just the compatibility condition between the differential and the bracket. So if I act with the differential on the bracket evaluated 2 objects, I can just move it inside according to the Leibniz rule. The only thing that is unconventional in this formula here is that the signs sort of look funny. So if I would want to write this as a normal Leibniz relation, I have to bring this term here to the left-hand side, and then there would be an overall minus sign. So that sign looks sort of funny, but that's just an artifact of the conventions I've chosen, the B-picture conventions, which are not the nicest if you want to directly connect to differential graded Lie algebras, but they are very much more convenient for all kinds of other applications. So if you don't like this, there's a different set of conventions called the L-picture conventions, in which one has a direct generalization of a differential graded Lie algebra in the sense that the L-infinity axioms look exactly like those of a differential graded Lie algebra, plus, of course, higher brackets and higher relations. Okay, now the third L-infinity relation, excuse me, is the one here. So here we have three terms, B2 squared. B2 squared, now let's go back to the basic formula here. So here I wrote out how to act with B2 once. Now, if I act with B2 again, in order to get B2 squared, you can see what's happening. Now, let me just try to sketch here, B2 squared on x1, wedge x2, wedge x3. Well, that just gives me then a B2 acting on B2 on x1, comma x2, comma x3. And then, of course, plus 3 terms. Sorry for my handwriting. The iPad is standing in a weird angle. So this is just in normal Lie bracket language, would just be 2 nested commutators as you know them from the Jacobi identity. So in fact, B2 squared equals 0 is just exactly the graded Jacobi identity if you view B2 as a co-derivation. So this is a very efficient way, even for normal Lie algebra, just to state the Jacobi identity. It's that a co-derivation B2 squares to 0. And so this leaves us, this yields 3 terms, which are just the Jacobi identity terms. But now you have 2 more. You have B1, B3 plus B3, B1. Again, the B1, B3 gives just 1 term if you act on 3 elements, because the B3 on 3 elements is already just one vector in the original space X. And then you act with the B1. Meanwhile, the B3, B1 gives you 3 terms, because you have to move the B1 through with the Leibniz kind of rule. Okay, so that's the third relation. And that is sort of the most interesting one, or well, at least coming from the viewpoint of a differential graded Lie algebra and trying to generalize it, which tells us that the 2 bracket need not to satisfy the Jacobi identity. And so this explicitly shows in which sense an L-infinity algebra is a generalization of a Lie algebra or differential graded Lie algebra, where the Jacobi identity need not to hold for the 2 bracket, but rather the failure of the Jacobi identity, what's sometimes called the Jacobiator, is controlled by the differential and by the 3 bracket. So if the 3 bracket is 0, it's just normal Jacobi. But if it's there and there's a differential, you get these modifications of a Lie algebra. Okay.
Hi, Olaf. Just a time reminder. We have about 5 minutes.
Okay, I'm actually almost done. So this was the definition of the L-infinity algebra, and writing out a few relations, what this means in practice. You can also write these L-infinity relations in a closed form without this detour of co-derivations and co-algebras, etc., etc. The explicit formula is of sort of like of this kind here, where you have some sum over unshuffles and casual signs floating around, etc. So it's not very intuitive, at least not for me. So if once you've played a little with co-derivations, it's much cleaner what you actually mean. So that's the basic definition, and here are the first few relations. And once you've seen how it works, you gain confidence that you would be able to work it out to arbitrary order if you need to do it. Okay, just to finish today's lecture, I want to give 2 more definitions that are important. One is the notion of an L-infinity morphism. So I've defined for you the notion of an L-infinity structure on a vector space X. And now let's suppose we have 2 vector spaces, X and X prime, and both carry an L-infinity structure. You would want to know under which conditions they are sort of equivalent in some sense. In which, I mean, that the L-infinity relations are equivalent. And that, of course, important in view of the applications we have in mind for physical theories, where you want to understand in terms of L-infinity language when two physical theories are equivalent, for instance, in the sense of being relatable by nonlinear field redefinitions. So this is the notion of L-infinity morphism. So suppose you have, so an L-infinity morphism is a collection of graded symmetric maps, capital F. So that just consists of maps F1, F2, and 3. So having 1, 2, 3, and higher number of arguments from Sx to S of x prime. So you to take this symmetric tensor algebra again. So you have all possible powers of vectors in X. And so you can act with these higher maps F1, F2, and 3. We take them to be of intrinsic degree 0. And there are two conditions. First of all, this is supposed to be a morphism of co-algebras, which means that the co-products are compatible. So this is this equation here. So if you first act with the co-product to get something in S tensor S, and then you act with F, so in other words, you act with F tensor F, this is supposed to give you the same as if you first act with F and then you act with the co-product, which is now the co-product on the other space, which I call it, which is the reason I called it delta prime. And the second condition is that it respects the co-derivation, which is of course what you want, because it's supposed to respect the L-infinity structure that is encoded in the co-derivation. So just the comment, this first condition that you have a morphism of co-algebras is actually what determines how these sequence of maps acts on elements of S of x. So for instance, as before, we can ask, how does F act on a single vector x? Well, here just take F1 and evaluate it on x. That's simple. But now for a quadratic monomial, it's already slightly more subtle. If you have capital F on x1 wedge x2, you can, of course, say that's F2 of x1 and x2, which is the right kind of object. But you could also consider F1 of x1 wedge F1 of x2. And that term actually needs to be added in order to obey this equation up here, that you have a morphism of co-algebras. And you can check that this formula can be extended to arbitrary higher powers using this relation with co-algebras. Here's just a quick check that this works, but this is probably best if you do it by yourself. And here's the final definition I wanted to give just for completeness, because this is also something in general we need if you want to write actions for theories and interpret that in terms of L-infinity language, which is the notion of a cyclic L-infinity algebra. That's roughly like a Lie algebra with an inner product. So it's an L-infinity algebra equipped with an inner product, which is a map kappa from X cross X into R, so that you have a symmetry property, which is written down here. So if you sort of think of raising and lowering indices is intuitive. So you consider the pairing under this inner product of x1 with the bn evaluated on x2 to xn plus 1. And that's an operation that involves n plus 1 vectors. And the condition is that this is supposed to be graded symmetric. So for instance, if you exchange the order of x1 and x2, this is supposed to give the same or a sign if both are odd. So that's what we of course mean by graded symmetric. Okay, so that basically completes the first lecture. I hope I've given you a sort of understandable definition of L-infinity algebras. At the end of the day, you can sort of forget about all this co-algebra, co-derivation business, because the L-infinity relations can also be written explicitly. It's just my experience that actually that illuminates how these formulas work and makes it more intuitive once you've gotten used to co-derivations. But at the end of the day, it's something very simple. It's a vector space with a grading and a bunch of maps that satisfy relations that are exactly analogous to those of a differential graded Lie algebra. that we're all familiar with from Yang-Mills theory. So what I will then do in tomorrow's, the second and third lecture, is to first explain how field theories are described in this language. So basically the L-infinity algebra is precisely the right algebraic framework in order to define perturbative, at least tree-level classical field theories. And then second, I will explain the notion of homotopy transfer, which is a very natural algebraic implementation of operations that we're all familiar with in field theory, like the integrating out of degrees of freedom in effective field theory. Okay, let me stop here. Thank you very much.
Thank you very much, Olaf. Is it okay if I post a link to your paper with Barton?
Sure, absolutely.
I think so what you saw Olaf doing today, it's more formal, but then in this paper you can find some more practical examples, I would say. And Olaf will continue tomorrow. Now we have a break about 10 minutes, so we will reconvene at 3:15. So just let me say something. So if you want to have to ask questions during the lecture, the introductory talks, it would be fine to just unmute your microphone and do it anytime you want. No need to raise your hand or anything. Yeah? Later today, there will be a question and answers session with both Olaf and Barton. So you're free to come and ask as much as you want. And Olaf will continue tomorrow. So at 3:15, we'll continue with Barton. And if Barton is around, we could try your screen sharing just to see if it works. Hyperbolic geometry.
Thank you very much. Thanks for the organizers for an opportunity to lecture here. I'll be talking about string field theory, vertices, and hyperbolic geometry. In some sense, you could say this is a complement to what Olaf has been talking in his previous lecture and what he will continue to lecture. You may know that L-infinity algebras played an important role in the construction of string field theory, in particular in the construction of closed string field theory. And this is the subject of this talk, closed string field theory. And in a sense, there's two kinds of difficulties when you construct a string field theory. There are algebraic complications or challenges and geometric complications and challenges. And these algebraic complications and challenges are taken care by the framework of conformal field theory, L-infinity algebras, BV quantization. And on the other side, the geometric challenges have to do with Riemann surfaces, and they're of a different kind. And that's the subject of my talk, the geometric challenges. And but despite that, there's a remnant of these Batalin-Bielkowski structures that are related to L-infinity algebras here as well. So that Batalin-Bielkowski structure keeps organizing some of the geometry as well in a very nice way. So I will give these lectures, and this is the hope of what I will do. I will write as I talk, so this is just the summary. And in the first lecture, I will speak about what string vertices are, what is a geometric master equation, and discuss why string theory vertices should exist. That is going to be a little delicate, especially the existence of vertices is a rather intricate question, and one that I was involved over the last couple of decades on and off. And the fact that we have a better understanding of it now, I think it's something worth discussing, and I'm going to take the opportunity to try to explain that. So then in lecture 2 today, after a break of 15 minutes, I will try to explain some aspects of hyperbolic geometry, which provides a new solution for possible string vertices. Finally, in the last lecture, I will talk about the Feynman diagrams of hyperbolic string field theory, how it may be related to minimal area problems, and how we can get off the ground in doing off-shell computations. This was work of MIT student Atakan Hilmi Firat, who will be speaking later in this conference, but about a different subject. So that is the plan of the talk, and basically we're talking about string field theory vertices, and this is just essentially string field theory. Now, string field theory, you have open strings and closed strings, and I will focus just on closed strings. In principle, I will be discussing a geometric structure that underlies all of closed string theory. So it would be the geometric structure that underlines not only bosonic closed string field theory, but heterotic string field theory, type 2 string field theories, in which cases the algebraic complications are also notable and took some time to sort out. So basically, the subject of today is the geometry that underlies the closed string theories. So I have to define what string vertices are, and these are just essentially pictures that represent this elementary string interactions in the string field theory action. So the question of finding string vertices is the question of trying to figure out how to write a string field theory. So without further ado, I will begin, and we will be talking about Riemann surfaces. For example, a Riemann surface of genus G and n-marked points. So G is the genus, the number of holes in the closed Riemann surface, and n-marked points. The marked points are called punctures. These are just points that you select on the Riemann surface, and they represent the places where there will be insertions of the vertex operators of the conformal field theory that defines the string background. So this is a general tool. So here, this surface sigma Gn is one of many Riemann surfaces of genus G, and the whole collection of Riemann surfaces of genus G will put them in a space called the moduli space of Riemann surfaces of genus G with n punctures, because these surfaces are not conformally equivalent. There's no analytic map between two surfaces in general, two surfaces of genus G with n points. There's a family of them, and all of them are inequivalent Riemann surfaces. And the spirit of string theory is that amplitudes come from integrating over all surfaces, really meaning all Riemann surfaces, the correlators of vertex operators. So sigma Gn is some point here in this moduli space of Riemann surfaces. Now, if you would be doing, for example, a sigma 2, 3, that would mean genus 2 and 3 punctures. 1, 2, 3, for example, placed there. And that's the surface sigma 2, 3. On the other hand, that surface is not enough. It's not sufficient to do calculations in string field theory. you need to know how to insert the vertex operator. So actually, you need to define some way of putting coordinates around these punctures so that you can insert vertex operators. Now, you may have the impression, and this is true for on-shell string theory, that the on-shell vertex operators are conformally invariant, so you just insert them, and it doesn't matter what coordinate you use to insert them. These are operators O that depend on Z and Z bar, and you just use any Z that the Riemann surface furnishes you. But that's not true for general vertex operators that are not conformally invariant. You must know how to insert these operators in a well-defined way using some coordinates. So you need to define coordinates around the punctures. So this is done.
May I add one point?
Yes.
In the old day, when you used the Vesuvian procedure for on-shell amplitude, you needed also to have local coordinates. Otherwise, you missed the moduli space. So it's not completely true that on-shell you do not need local coordinates, at least when you start doing loops.
Look, the Riemann surface comes with a whole chart of local coordinates. So when you're working on shell, you can use any local coordinate associated to the puncture. So any local coordinate, any Z that vanishes at this puncture is legal to be used, and it will not affect your computation in general. There's small tiny complications with a few set of states, but in spirit, there's no need to select a local coordinate, which is what I'm going to do now. Look, here is the way you select the local coordinate. All you have to do is draw some curve around each of the punctures. And these curves should define disks that don't overlap. So once you've done that, we claim that we have selected a local coordinate around each of the punctures. So the one thing I forgot to say, of course, with questions, we proceed as Olaf and Renan told us, ask and interrupt, and we'll try to answer them as they come. So once you draw these things, you can draw any simple closed curve. Simple means no self-intersections around the punctures, and that defines local coordinates. How come? Well, for example, if you have the puncture P1 here, P1, P2, and P3, those are the names of the punctures. There is a map unique up to rotations that maps this disk around P1 to we can call this the function H1, to a disk W1 of radius 1 with the puncture P1 at this point. This map of the arbitrary disk around P1 into a canonical disk W1 less than 1, this map is unique up to rotations. You know that because there are 3 parameters in a map from 2 disks to each other, and 2 parameters are used to force the puncture to end up at W1 equals 0, and 1 parameter represents a global rotation. So this defines coordinates, because here you have little coordinates, and this map that is invertible defines the local coordinates here. So when you insert the operator, say O1, you must insert it at W1 equals 0. And if there is a coordinate Z in here on this Riemann surface, This thing is the conformal map of the operator O1 from Z equals 0, which is a coordinate defined on the Riemann surface arbitrary coordinate there. So when you have to do correlators, you must insert the vertex operators at the local coordinates equal 0 for the selected local coordinate, which is the shape of that curve that you draw around the punctures. And then you transform the operators from W1 equals 0 to a coordinate Z. For example, if this would have been a sphere, it would be very simple. You can use the Z coordinate on the sphere. If it's a higher genus surface, as Igor was mentioning, it's a little more complicated because you can only cover the surface with patches. So at any rate, this is the spirit, and adding this information turns the surface, we put a hat on it, and we say that there's a space here that we call P hat GN of surfaces with these curves drawn around each of the punctures. And there's infinitely many ways of drawing this curve. So while the space MGN is finite dimensional, in fact, the dimension of MGN is 6G minus 6 plus 2N. The space P hat GN, which is the space of all Riemann surfaces with all possible choices of curves around the punctures or local coordinates, is infinite dimensional. You can think of it as fibered on top of MGN. And over here, you have a surface sigma GN hat with some particular choice of local coordinates. If you forget the local coordinates, you have a map pi, which is a forgetting map that maps PGN to MGN. So over every point on MGN, there's the fiber, which corresponds to all possible choices of fibers that you can put there. Okay, so we've defined PGN and MGN, and now what are the string vertices? Well, the string vertices, again, we start with MGN, and we have PGN. The string vertices are supposed to be, I'll use this color, a little piece. We can draw it like this, say, and I'll call them nu GN. This nu GN is a string vertex for genus G and N punctures. So this is a string vertex. Nu GN, and it represents a collection of surfaces. If you use the pi map that takes you down, you could say that this is a collection of surfaces that you need to add to the elementary string action to produce a consistent theory. This is a vertex, represents a term in the action. These are the Riemann surfaces that previous computations didn't manage to produce with Feynman diagrams, and you were missing a piece of moduli space, and here it is, you must add this to the elementary action. So this nu GN represents a collection of surfaces with local coordinates, so it's some curve in here on the space PGN, and represents a collection of surfaces that we have here. So it's an elementary interaction. So what are these string vertices? Well, you should start. We're thinking classical theory. It turns out you could say, well, you need maybe spheres with no punctures, sphere with one puncture, sphere with two punctures. That's not true. The first one that you need is genus 0, which is spheres, with 3 punctures. It's a 3-point vertex. There's no need for a sphere with 2 punctures. There's a deep reason for that. The BRST operator and the algebraic structure of the theory takes care of it. And there's a reason that it's related to hyperbolic geometry or to geometry in general, but you just need the 3-point vertex. You probably need a classical 4-point vertex, a classical 5-point vertex, and all those. At higher genus, you still are missing some regions of moduli space, and the ultimate logic of this comes from the Battalion-Milankovitsky master equation. So you're missing nu 1, 1, genus 1, 1 puncture, genus 1, 2 punctures. And in particular, you don't miss genus 1, 0 punctures. That again, the string field theory doesn't require that. And that's kind of nice because there was a lot of debate in the early literature in string theory by Polchinski and others that the vacuum graph could never work and therefore a string field theory could never exist. In fact, the string field theory avoids this problem and associates no surfaces required in the action for genus 0 and no punctures. And then it continues actually for genus 2. You can introduce no punctures and surfaces like that. So just like Olaf was summing over vector spaces, we are going to sum these new GNs are surfaces. There are subspaces of PGN. So we're going to think of spaces of moduli spaces in which you put together the moduli spaces of these surfaces and those surfaces and all the surfaces together, and you can sum spaces on different moduli spaces. So you will define a general vertex nu, which is the sum over G and N of H bar to the G nu Gn. And the constraints for N and G are those that I've shown here. That is, for genus equals 0, the sum goes from 3. From genus equal 1, the sum of N goes from 1 up. And for genus equals 2 or more, it goes higher up. It is interesting from the viewpoint of hyperbolic geometry that all surfaces in these moduli spaces that we're looking at admit hyperbolic metrics. A hyperbolic metric, we can get started with this hyperbolic metric.
One question.
Yes.
The motivation behind identifying this region in the PGN section for the elementary interactions or string vertices, is it that we want to write it, we want to write for any genus order as a 1PI effective action, or is there any other motivation? The motivation behind identifying these different regions in GN?
Well, these vertices that we're identifying is not quite, by the time you go up, it's not quite the logic of 1PI actions. 1PI actions you sum over some particular part of the Riemann surfaces. Here we're going to write what we call elementary actions, actions that solve the Battalion-Milankovitsky equation. So we will not just reduce to a 1PI action. Well, that is a more sophisticated construction. You start with an elementary action that has all interactions, and you can construct the 1PI. We will construct the basic string action. Okay, so hyperbolic metrics exist.
Barton, I have one question. Yeah, do you really need the 0-point function from field theory viewpoint?
No, I don't need them. So even though they are here, and we can introduce them in the recursion relations, we don't need them for writing the action. They would produce constants. Now, as we work together, I think that is a point. If you include those constants, you have a better control over the background independence of the theory. That is, those constants with interact, whenever you shift background, the 1-point functions contribute to those constants, and they reproduce the partition functions of the conformal field theory to that order. So somehow in a background independent formulation, those constants may play a nicer role, I think.
I see. Oh,
but yeah, I don't think, yeah, it's nowhere in the calculations of the action or the consistency, those seem to play a role.
Yeah.
So in the hyperbolic metrics, we have this, and those have Euler number 2 minus 2g minus n for any new gn, and all of those for the surfaces that we've pointed out above are less than -1. So there's no hyperbolic complete metric on a sphere with 2 punctures. It's or things like this. This doesn't quite work. Now I'm going to get into a point that is a little sophisticated, but I think it's interesting, and I want to emphasize it because I think it's part of the story, is that one must work with homology. In homology, you think of spaces, and you have things called chains, which are subspaces, and in those subspaces are considered, you take boundaries, and that's the action of the boundary operator on the chain, the boundary, if a boundary is 0. So in general, you work with chains on PGN. Now, those so-called subspaces are chains, so we would say new GN belongs to chains on PGN. It is an interesting mathematical point that this should be something I don't have great intuition about it, but some I do, singular chains. So what is a chain? You have a simplex, and you map into the space PGN in this case with a function, and the image of the simplex on the space is a chain. Now, we as physicists tend to think of these spaces as very nice ones, but in fact, more is true, and sometimes more is needed. For example, if you have an MGN here, it is possible that the new GN could be not just as simple as this, but rather it could be a space like this. Now, that's nothing too bad, except that there seems to be surfaces that map 3 surfaces that are a surface that is produced 3 times, but in general they are produced with different signs and they have no big problem. Now, even that is not so serious or so complicated. And we can say, okay, that's no problem, but how about this? Now, this, not if it has self-intersections, is not quite subspace, a manifold. So singular chains allow for this, a thing that has things like that. Or it allows for MGN, and you may have a vertex that is this, but actually you use a superposition of vertices with different weights. You want to produce a chain that is some collection of surfaces where you produce 1/3 of these surfaces, 1/3 of those, and 1/3 of those, and that's fine. It's a general chain. So we can work with these chains, and everything is good. So this is the theory of singular chains, and a mathematician looking at this problem definitely would use that. And I think it's interesting that in using superstring field theory, where you have to insert picture changing operators, more complicated situations, perhaps like those shown here, and definitely like those shown here, are necessary to write the string action. Moreover, there's one more condition that sometimes is mentioned in passing, but it's also important, that we must work, if you're working with PGN, with SN invariant chains. Chains, again, is this generalized subspaces. SN invariant refers to the action of the permutation group on the labeled punctures. So a Riemann surface comes with labeled punctures because you have a collection of vertex operators. You're going to insert the first vertex operator, the second, the third, the fourth, and you just go on. And if you have a particular Riemann surface with some number of punctures, the ones where the punctures are labeled different must be included in the chains. So we have SN invariant chains. And that's important. Somehow the string field theory, in a sense, forces that to you, but we probably want to include this. So we say that nu GN belongs to the chains that are SN invariant. So,
Barton, I have one more question.
Yes.
Is there any problem if we use vertical segments, or that's also should be okay?
I think there's no problem whatsoever if you use vertical statement. It's a generalization of this thing, in which you sort of, here you have a little piece that is vertical, so it could extend to more things. So that should be no problem.
Okay. Okay. Thank you.
Sure. All right. So I'm going to continue with this. I'm going a little slower than expected, but that was.
Can I ask a question as well?
Yes.
Hi.
Yes.
So the insertions in VGN, are they really vertex operators, or are they the full string field, which can be expanded in given basis?
They are string fields. If you're talking about the action, you insert the whole string field, but by linearity, the string field is a sum of numbers times vertex operators. So
then would this symmetry be sort of manifest?
It will be implemented manifestly, yes, by the end of the day. So the parts of the chains that are not...
It should be automatic.
Yeah, it should be automatic, but at the end of the day, if you want to define the vertex that really contributes, it's a symmetric chain. So it's either 0 or it's not 0. So, but indeed, if you put into the action something that is not symmetric, the action will pick out the symmetric piece of that. But if you're talking about chains, it makes it a lot more complicated if you don't assume it's symmetric. In fact, we will see why that is important in a little while.
Okay, thank you. But
that's absolutely true. So the string action is defined. So here is an important thing. The string action string action, you have a string field psi that lives in the conformal field theory state space. And we write the string action determined by the vertex. Remember this vertex we have here. We call it nu from now, this formal sum. And this string vertex helps you define the action in the following way. You have an S02, a kinetic term, plus an action, that the part of the action that depends on the string field and the vertex, which is this. And this is defined linearly in the Riemann surfaces. So in such a way that I just need to tell you what it does on nu gn. And without getting into details, is the integral over nu gn of the correlator of these string fields located at these end punctures over the moduli that describes this nu gn. So it's the integrated correlator over the surfaces in that thing that we call the a piece of a section over mgn. And so the next point is to explain that there's a Battalion-Vilkovisky structure. Battalion-Vilkovisky structure. So here it is, if you wanted to know why the vertices are important, it's because with the vertices, you can define the action. Now, what is S02? Is the familiar psi q psi term in the action. So a BV structure, a Battalion-Vilkovisky structure, is defined with operators boundary. Well, actually, I will not do that one. This is not quite in a Battalion-Vilkovisky structure. There's an anti-bracket and a delta operator, which is a second-order derivation that squares to 0. Now, curiously, that Battalion-Vilkovisky structure can be defined on surfaces, on Riemann surfaces. And this is work of Ashok and myself. And for example, if you have two Riemann surfaces, sigma 1 and sigma 2, and you wish to compute their anti-bracket, you basically take the first Riemann surface, pick one of the punctures, the second Riemann surface, pick one of the punctures. Remember, these are surfaces on PGN, P hat GN, so they have local coordinates. So what you do is cut out, cut out this disk, cut out this disk, and glue the two surfaces across the boundaries and twist them by an angle theta from 0 to 2 pi. So it's really essentially here the union from theta equals 0 to 2 pi of the gluing of these two surfaces with a twist theta. And if you have many punctures, you must do over all punctures this gluing. And therefore, from two surfaces, you get one by gluing them in this way. There's another operation called the delta operation. I'm sorry, I said here defined on Riemann surfaces. So there's the delta operation that takes a Riemann surface that has at least two punctures with local coordinates, and that's kind of the same thing. Cuts out these disks and glues them so that you produce a new handle by gluing the boundaries and twists them by an angle theta. So these are the two operations, two different surfaces glued together and twist across using these coordinate curves, and a single surface, two punctures, glued, twist. Now, you can apply this not just to surfaces, as we have it here, but to moduli spaces. So you can put a moduli space here and a moduli space here, and then you're supposed to do this over all the surfaces, for every surface in the first moduli space and for every surface on the second moduli space. You glue and sew together and twist over all the punctures. Well, that's a lot of operations, but it can be done. Also, delta acts on moduli spaces. Finally, since you act on moduli spaces, a natural operation on moduli spaces is the boundary operation on moduli spaces.
Can I just check one more thing? Is the location of these punctures integrated in your gauge slice, or are they fixed?
Yes. So yes, the location of the, you see, when you fix the vertex, you fix the set of surfaces that have the punctures at particular locations. So as you move along the vertex, the position of the punctures is changing, and the conformal structure of the underlying surface is also changing. Now you just get a piece of the moduli space. So the integral at the end of the day must be over all moduli and over all positions. But in the vertex, the positions of the punctures and the local coordinates around them are all fixed.
Sorry, I thought so they are fixed. I mean, the location. Sorry, I thought you said that the one integrates, but.
Oh yes, basically what I'm saying here is that on every surface here that you pick one surface that has the position of the punctures fixed. On another surface on the vertex, the positions are elsewhere, and the complex structure is changing. But on each surface, the position is fixed.
So the curvature of the underlying surface will be important as well, I guess, if there is curvature.
Well, these Riemann surfaces have a Gauss-Bonnet theorem. Now, as Riemann surfaces and local coordinates, the curvature doesn't play any role. The role of the curvature is to help you invent the local coordinates, basically. You see, nobody tells you how to draw those curves around the punctures. And the best way to draw curves around the punctures is to put a metric on the surface and use the metric to define those curves. So that's why we use metrics, not because of any reason. The whole discussion could have been done just in terms of Riemann surfaces.
So the metrics will be the hyperbolic ones that you can discuss, I guess.
Yes, today we're going to discuss the hyperbolic ones. Exactly.
Okay, thank you.
Yes. Okay, so let's get to this part of the punchline, because we probably need to get a little further. So we said, okay, defined on Riemann surfaces, and number 2 is defined on functions of HCFT. So these are the familiar anti-brackets, because in a conformal field theory, there's a lot of vertex operators, and there's a nice way to produce a pairing between them to define an anti-bracket and all these things. So if you think of the string field as the sum of coefficients times vertex operators, OI, the TI play the role of space-time fields, and these are the conformal field theory operators. The I nu of psi's are, in fact, functions of the TIs because they calculate the correlators and the operators are done at the end, and it's an action that depends on the space-time fields. And the nice thing about this correspondence is that the Batalin-Vilkovsky structure that exists in the conformal field theory allows something very nice to happen. If you have to calculate the function associated to the moduli space that comes from the anti-bracket of these two moduli spaces, this is the geometric anti-bracket I just introduced, this thing is equal to the conformal field theory anti-bracket of the two functions. So the anti-bracket here on the left is geometric. The anti-bracket here is algebraic because the I are functions on the conformal field theory space. So here you use a conformal field theory anti-bracket. Here you use the Riemann surface anti-bracket. Moreover, I of the boundary of nu, of that moduli space, turns out can be calculated using the BRST operator, the quadratic form, quadratic term in the action. So it says 0, 2 with I nu. And finally, I on delta nu is just delta acting on the function. So the deltas, the anti-brackets are different, but they talk to each other geometrically and algebraically. So,
sorry, just a question. When you talk about the anti-bracket in conformal field theory, do you mean the anti-bracket you can compute from quantum field theory normally when you consider, since you are saying that I is a function of the T's. The T's are essentially quantum field theory or quantum fields. So the anti-brackets you are talking about in conformal field theory is the anti-brackets in the quantum field theory, or what else?
Yes, it's a very good question because I'm going a little sketchy, but here it is the way it goes. All the TIs those are the space-time fields, can be split into two collections, T tilde i's and T double tilde i's. So you split all the space-time fields. The conformal field theory tells you how to do that in such a way that one of them can be thought as fields, the other anti-fields. And then it becomes the standard BV anti-brackets, partial derivatives with fields, partial derivatives with anti-fields, and all these things. So basically, the conformal field theory allows you to see which T's are fields and which T's are anti-fields.
Okay, thanks a lot.
Great. So basically, here it comes, the main conclusion. You want the action that we've written to satisfy the master equation of Batalin and Vilkovsky. So if your action satisfies the master equation of Batalin and Vilkovsky, you have a consistent action for defining observables, quantization, all these things. And then, since these anti-brackets and all these things involve nu, there's a constraint on nu And this is that actually this equation we've written holds if and only if this equation holds for the spaces. And we call this the geometric master equation. And so in this equation, boundary is the boundary of a moduli space. The anti-bracket is this thing. You take the surfaces and glue them, and the delta takes each surface 2 punctures and glues them, and this whole operation must be 0. And this translates the Batalin-Vilkovisky master equation for the action into a constraint for the vertices. So this equation, basically, this equation implies the desired equation. So if your string vertices satisfy this geometric equation, your string action will be in good shape. So in a sense, this is the equation we want to focus today and tomorrow on solving, finding vertices for this equation. Now I want to discuss this and say a few comments about this because it's important. So finding vertices is finding a solution of this geometric master equation. And we know that we must start with nu 0, 3 and go on. The next thing, the solutions of this geometric master equation are not unique. If you find a collection of vertices, you can deform them and find another one. And in fact, if you have one solution, you have infinitely many. These are obtained by doing canonical redefinitions of the string vertices, canonical in the sense of the anti-bracket. I will not discuss them. Actually, in this paper, that I'm really, a lot of what I'm saying today is based on this work I did with Ashok long ago, and this revisiting of all these issues in a work with Costello, which, since he's a mathematician, I actually learned a number of things about how to think about these subjects in a more abstract and perhaps more powerful way. In fact, with him, there's a few other things that can be shown about this equation, but I will focus on one question, the question of finding solutions of this equation. So why do we want explicit string vertices? Well, you want explicit string vertices because then you can write an action and then you perhaps, for example, can find classical solutions. It becomes an important question because in some sense, if you find a nice set of vertices, you might have a better chance of finding a classical solution. If you don't have an elegant set of string vertices that satisfy some nice properties or come from a nice principle, it might become impossibly hard to find classical solutions. Same thing for the computation of off-shell amplitudes. A good set of vertices should make this more doable than a haphazard set of string vertices. If you want to compute the action and sort of resum the infinite series that the action defines, again, with a nice set of vertices, you may have a hope. If you don't have a good set of vertices, well, you won't get any insight from explicit calculations. They won't help because the vertices are a mess. So finding nice vertices is important. If you think of the classical solutions that have been found so far in string field theory, they all come from the Witten associative form of the open string field theory. And there are non-associative forms of the Witten theory with more general vertices, and nobody has found a classical solution with those in a nice way. You could always say, well, they're filled with definitions of the others, but nothing becomes simpler or nicer. But on the other hand, with the Witten vertex that is associative, you manage to invent things that make it work. So for example, for closed string field theory, it still remains to be shown, but at least my prejudice is that finding a classical solution, as people could do for the Witten string field theory, requires a nice set of vertices, and probably the vertices that come from polyhedra and minimal area may be the nicer ones for a classical solution. That remains to be seen. I will talk today about the hyperbolic solution that has its own elegance, but even the hyperbolic solution has its elegance in many ways. It's very elegant, and therefore may eventually lead to all kinds of insights. In terms of classical solutions, the hyperbolic version of open string field theory is non-polynomial, and I don't think anyone has said anything simple about classical solutions in this case. So it's a matter of finding a good way of doing things. Now, there's a set of very simple vertices called projective or SL2R vertices that for low dimensional moduli spaces, they are simple, but then apparently they get extremely complicated at higher orders. And so if your computations are low order, you can do great progress with those. But then if you want to work to all orders in string coupling or do the whole classical theory, it might be fairly difficult. So how did physicists approach this problem of finding string vertices? A mathematician would have done it differently. A mathematician would have said, here is the geometric master equation. First, I'm gonna show that solutions exist. And then I will try to find some solutions or leave it up to some practically minded person to do that. Physicists, we all kind of suspected that solutions to this master equation would exist, and we had vague arguments why. And we had all kinds of arguments that there were procedures that could be done recursively and thinking about it. And we don't have any clear picture of how to prove that these solutions might exist. So we proceeded to try to find solutions, and we found some partial solutions with minimal area metrics, very nice solutions for the classical theory, less simple solutions for the higher genus theory, but not complete solutions, and no complete proofs that the solutions exist, although I think everybody would bet they do. And then a more recent attempt.
Just a time reminder, 5 minutes before the break.
Right. A more recent approach was done by Pius and Musavian, who insisted in using hyperbolic geometry and did a lot of nice work towards formulating a hyperbolic string field theory. Our contribution, Costello and I, to this was to simplify the form of the string vertices they were using. And that will be the story I will be describing now. On the other hand, I want to actually do for fun the discussion of existence of the string vertices. Again, Costello did that on a paper in 2007, I think, and his proof of existence was about 5 lines and was pretty difficult to understand. So actually in our paper a couple of years ago, we decided to write it all out and kind of explain this proof. So I thought it might be fun to just get an idea of what is involved in explaining these things. So this is what I will discuss now. So I will introduce the question and discuss it over the first part of the second talk, and then turn to hyperbolic geometry. So the question is the existence of string vertices. Vertices.
One question.
Yes.
In the previous, where you showed the relations of I delta nu is equals to minus delta phi nu, those relations, can you put it?
If Renan could understand the question, or somebody, I cannot understand.
No, I'm referring to the part. Yeah, I'm referring to the part where you wrote down the relation. On the left hand side, you had the geometric operations. Yeah. This question, I delta nu. So on the left hand side, this delta operation is like gluing two punctures on the same Riemann surface.
Right.
And on the right hand side, this delta is like the some derivatives with respect to the fields and anti-fields, right? So
exactly.
In terms of which. So this is like a definition, or this can be shown explicitly, this relation?
This can be shown explicitly from the correlator. So you define, we've defined delta on surfaces, we define delta on the TIs, and then you can prove this. So these are not postulates, these are proofs.
Okay.
Great. So existence of string vertices. So we will, I will go one more minute. We will fix the first one, nu 03, that belongs to p hat 03, and it will be S3 invariant. And we'll try to solve for the nu GNs. And we will work recursively in the dimension of the spaces. So dimension of the moduli space nu 03 is 0. The next ones, the dimension of nu 04 or nu 11, one puncture torus, are both equal to 1. Then there's spaces of dimension 2, and we will work recursively in that way. You can check, and this will be kind of the basis of what we're going to say, that if you take the master equation, the geometric master equation, and take this other terms that are not the partial of nu to the other side, you can then check that since you expect, since d of d is equal to 0, you expect that d of h bar delta nu minus plus 1/2 nu should be 0. You would expect that, and indeed you can show that that follows by using again the geometric master equation. So if the geometric master equation holds, this will be correct. So I will write one more equation, and this is the following. If I write this explicitly by saying d nu gn is equal minus h bar, well, actually no h bar here, minus delta nu g minus 1 n plus 2. You see the delta operation increases the genus by 1, so it must act on a moduli space of surfaces with genus g minus 1, and you lose 2 punctures, so it must act on a moduli space with n plus 2 punctures. Minus 1/2 sum over g1 plus g2 equal g, n1 plus n2 equal n plus 2, nu g1 n1, nu g2 n2 And that's it. That's the equation in general. So what the last thing I'm going to claim is that before we really get started with the problem is the following, that this computation I've done here, the mechanics of this computation is clear that if you're working with some space nu GN here, all the spaces that are in here on the right-hand side have lower dimensionality because the twisting adds one more dimension. So they all have to have lower dimensionality. So in a recursive procedure, all the right-hand side involves spaces for which you've already checked that they've been constructed and they're good. So the only question remains whether you can construct the next space based on spaces of lower dimensionality. But you can also see that the boundary, if you call this right-hand side OGN, the definition of the right-hand side, then the calculation I did before of checking this stuff implies that if the moduli spaces on the right solve the master equation, the boundary of OGN must be 0. And that's something you should be able to calculate and prove. So I will stop here. It's the beginning of the proof, and we'll take it a little later, but I think I've overextended myself for 4 minutes. So thanks, Brennan, for the patience, and we will retake this in a few minutes, 10 minutes, or whatever you say. Thank you.
Okay, thank you very much, Barton. So we'll reconvene. I think we can reconvene in 5 minutes. Yeah. But no, it's okay. Well, let's do 10 minutes then at 4:30 local time here.
What time?
4:30 in 10 minutes.
10 minutes. Perfect. Very good.
It's okay. Thank you again, Barton. See you soon.
Very good. We constructed a formal object, which is the sum of those vertices. We decided we would work in homology with singular chains of Sn invariant chains if you have n punctures. And we showed that there's a Battalion-Vilkovsky structure on the you can induce in the Hilbert space of the conformal field theory, one on Riemann surfaces. They tie together and make it possible to put the condition of the action solving the master equation into just requiring that the string vertices solve a geometric master equation, which is a set of recursion relations. We said we would solve for this vertices recursively in the dimension of the moduli spaces. The zero-dimensional moduli space in the string vertex is the 3-string vertex, is the most important vertex of all. And after you have that, you presumably can calculate the nu 0,4, the 4-string vertex, the nu 1,1, which is the genus 1 puncture. And what we were saying was that if you're working recursively, you can write the equation at each order in this form, in which the boundary of the nu GN that you now want to calculate, it's a space with one higher dimension than the ones that you've already determined. The boundary of that space is defined by this right-hand side that only involves spaces of lower dimension that already satisfy the master equation. And whenever spaces satisfy the master equation, you can show that the boundary of this OGN, this right-hand side, is equal to 0. That ultimately follows from this fact that I mentioned before, that if you take this object, the derivative of it, the boundary of it is 0 by using the master equation. So if you just involve lower dimensional spaces, the fact that they solve the master equation similarly guarantee that the boundary of OGN is equal to 0. So the question is now whether you have an obstruction. And what would be an obstruction? An obstruction would...
Actually, sorry, before you get to that, could I just check? Is
Sure.
the geometric master equation valid for these vertices in particular, or does it also hold for the full moduli space? If you replace VGN by MGN?
No, it is supposed to be for these pieces of the moduli space, and that's all you need. The full moduli space will arise afterwards from the action when you calculate the Feynman diagrams and you put a propagator between these vertices, then you will generate the whole moduli space. Now, actually, that is a very interesting fact, and you would say, well, does it hold only if these nu GNs are nice sections or not? In this paper with Costello, we also wrote a proof that if the geometric master equation holds, the Feynman graphs thought as adding annuli as you glue things will generate a copy of the full moduli space. So that's something that will happen also automatically. So it's good to know.
Mm-hmm. And could you maybe say just a comment on what goes in the derivation of the geometric master equation? How does one derive it? Just briefly.
Well, the only derivation that I gave here was if I want the action to satisfy the master equation, which you do. If you want this action to satisfy the master equation, given all this interplay between geometry and BV in the geometry and BV in the conformal field theory, the requirement for the action S to satisfy the master equation is that nu satisfy the geometric master equation. So it's not like I derived it. I derived that this is the condition that nu must satisfy.
Okay, so it comes from the BV equation, equation for the action.
It's the equation that guarantees BV. And then sort of when you unpack it, you discover that it also guarantees that you cover moduli space and you're going to get the right sort of answer for the string amplitudes.
Okay, thank you, thanks.
Sure. Okay, so what is the possible obstruction? Well, we have to analyze if there is, if this space OGN represents some non-trivial homology on the moduli spaces of Riemann surfaces. So it's possible that this would be some homology group 6G minus 6 plus 2N minus 1. Remember, this is the dimension of the moduli space, nu GN, but this has boundary of nu GN, so it should be one dimension less. The index down here is for homology. And here we have, so it should, PGN hat of Sn. So here is what could happen. We are talking about OGN is some space that is, or some singular chain, if you want to speak mathematics, in PGN hat. And this PGN hat has homology. And if it has a homology, the only relevant homology is the Sn invariant, the permutation invariant homology. If this homology is non-trivial, it's a sign of danger that you may not be able to solve the equation that you're trying to solve. You're trying to solve the equation d nu Gn equal OGN. And this can be solved if OGN is trivial in homology, but if it's non-trivial, if there's a homology class, you cannot solve it. It's not a boundary. So basically, if this homology group vanishes, then OGN is trivial because OGN is a cycle. It's killed by the D operator, but then it's a cycle itself if it's trivial, if the homology thing doesn't exist, and it's the D of some other object, and then you simply can set nu GN to this order equal to KGN, and you've solved the question. So if you solve for this, this will solve the master equation, and then you can continue recursively. So the real question is whether this homology group vanishes, or more in particular, you want to show that, wish to show that this HG 6G minus 6 plus 2n minus 1 of P hat Gn Sn is equal to 0. So this must vanish, and back to this issue of symmetry, it might, if somebody comes and says, look, the homology group vanishes even if you don't put the permutation constraint, then that's good too, because if the homology group vanishes, putting the constraint is not going to create homology classes. So on the other hand, it may happen that the homology group does not vanish in general, but once you require that the chains be symmetric, the homology group will vanish. And actually, that's sort of what happens in the only place where it matters. So we will try to see that. Now, of course, I will not be able to prove all these things, but I want to show you how it just goes to give you a flavor of how it all works so that the roadmap is clear. I will therefore begin with claim 1.
One question.
Yes.
This homology group, if it is non-trivial, then it's the obstruction to solving these equations perturbatively or in general, like there will be non-perturbative solution also.
Well, you know, if this obstruction exists, then you're stuck. You might have solved up to the fifth string vertex, but then you cannot go on. So you can call it perturbatively. We perturb with sum over number of punctures, that implies the string coupling, with sum over general, which is over H. So basically, it's an obstruction to constructing the action. I think it's not just, oh, it's a perturbative problem, and now you can find the action some other way. We don't have any other way of finding the action. So it's a fatal obstruction. Oh.
Okay, thank you.
Okay, so my first claim is that we can work with a simpler space. P hat Gn is actually homotopy equivalent to MGN. This is probably well known to mathematicians, and we still gave a proof of this fact. Homotopy equivalence between spaces basically implies two spaces, a map from one to the other, a map from the second to the first, such that the compositions are inverses on the respective spaces. And what one gains with homotopy equivalence is that the homology groups are the same. Groups are the same when you have two homotopy equivalent spaces. Same. There's a book on algebraic geometry, Hatcher, I think it's free over the internet. This is the theorem, page 110. That once you have homotopy equivalence, the homology groups are the same. And the homotopy equivalence is not all that complicated. It's basically saying the space with, I'll say it in words, what are the steps? The space PGN is space with disks around the punctures. It's the same thing as the space of surfaces with boundaries and a coordinate, theta coordinate around each circle. The different spaces are different thetas, but they are all contractible. Any choice of thetas can be turned into any choice of theta by homotopy. So the choice of theta doesn't really make a difference in homotopy. And then this is equivalent to the space of Riemann surfaces with boundaries, but the space of Riemann surfaces with boundaries is a direct product of the moduli space times real parameters that represent the lengths of the boundaries. Those real parameters, again, don't matter in homotopy, and you can neglect them. So at the end of the day, this very large space, infinite dimensional, P hat GN has the same homology groups as MGN. So what you want to show...
Barton, so
yes.
here I presume you have to use the fact that you are using local coordinates up to phases, because it shouldn't work if you fix the phases, right?
That's right, absolutely. And from the very beginning, I mentioned just curves around the punctures and no special points selected on the curves. Absolutely.
I see. So that information goes into the proof?
Yes, absolutely. It goes into the proof. It's necessary for the proof. So it's P hat GN. Now, so therefore, we need to show that H6G minus 6 plus 2n minus 1 of MGN is equal to 0. That's what we need to show. Now, here things, get a little more interesting, and I think actually the proof that we give with Costello is all very nice, but still could be enlarged by a couple of pages if one wished to make it very clear to people that have a physics background. So here it is. There's Poincaré duality. So we go from homology to cohomology. And if you are codimension 1 here, this group is isomorphic to the first cohomology group of MGN. So by Poincaré duality, H6G minus 6 plus 2n minus 1 of MGN is just the first cohomology has the index up there of MGN. So this is the thing we would wish to make sure is 0. Now, it turns out that this non-compact spaces, this MGN, everything seems a little easier if you use the compactification version of these spaces. Again, being rigorous here is, it takes, I think it's a little difficult. I myself don't feel that 100% sure about some issues of rigor, but the step that one goes at this point is relate this to the Deligny-Mumford compactification of moduli space. That is a compactification in which the singular surfaces are becoming more and more singular, and you add one point or one surface, which is what is called the noded surface, a surface with a node. I could tell a bit more about this. There's interesting stuff with nodes, but this is called the Deligny-Mumford compactification. And this homology group, the cohomology group, can be thought, you can think intuitively both homology or cohomology, things are very similar. You can think of it as, I'm sorry, I have to introduce one more thing here. Here is the linear-Mumford compactification. But in a sense, you really want the homology of the original space. And this is captured by what is called the relative homology or relative cohomology, in which you use a compactified space and relative to the compactified surface, to the noded surfaces, the surfaces that you had to add to seal off the moduli space, which are MGN minus the whole bulk of MGN. So this is a relative homology. Let me say it again in words. The first element is the compact version of the moduli space. And here is the noded surfaces, the surfaces in MGN minus the MGN here. So these are just the singular noded surfaces. And this is a way to compute the cohomology of the original non-compact space. And let me just say a little bit of this thing. If you have a subspace A, a subspace of X in a manifold, there is this cohomology or homology, whichever you wish to consider, of XA, which is intuitively the homology elements on X that avoid A. So in a sense, chains in A are trivial. If you have a chain in X, it's a chain that extends everywhere, but you can subtract the chains in A and you're still in the same homology class. So this is a way to sort of figure out how much homology there is in a space when you take away part of the space. That's the A part. So that is the spirit in which this relation holds, that to figure out what there is in the space without compactification, you take the compactified space and think of the homology of the whole space minus the compact boundary. So this is the term that we must consider. So we want to show that this homology class is zero. Now,
may I ask a question?
Yes.
Why we don't want to consider the Mumford linear compactification? In a certain sense, it is a degeneration of a surface, which could be a degeneration of a physical meaning. It could have a physical meaning, this kind of degeneration, such infrared with particle propagating with very long distances inside the loops. So this is one question which I'm not completely.
I'm not sure what the question is.
Why shouldn't we consider the Mumford linear compactification? Why we should consider the MGN?
Yeah. So here, you know, this is the equivalence that I'm kind of trying to argue here is an equivalence that comes from mathematics when you compactify a space. Now, independently, why do we consider the linear-Mumford compactification? Well, this is the one that sort of comes naturally from string field theory. When you saw Riemann surfaces, you have sewing of coordinates in which you have z times w equal t. And t is a number that goes from a complex number in the unit disk. And the t equals 0 when it's a singular gluing is the thing that must be explained a little bit what it means, and that's what the linear did with this compactification. So it's a natural compactification that comes from covariant string field theory. It doesn't happen, as far as I know, in light-cone string field theory. You don't have that, but in covariant string field theory, it sort of comes natural to you. It might be that in special gauges, you can do string diagrams with special gauges where this sewing doesn't quite apply or is more complicated, but certainly this is very natural for physicists. So
okay.
I don't have much more to say.
No.
Barton, maybe I have a related question, which is that suppose you take one puncture and go around the other in a circle.
Yeah.
That looks like a non-contractible cycle, right?
Yes.
So that doesn't cause a problem here?
We will see that kind of possible trouble in a little while, in fact.
I see. Okay.
I have another question. When you talk about homology or cohomologies, you have to specify whether you do it on the real or over the integers. So are you doing the cohomology over the integers or over the real? Because if you do over the integers, you can also have issues with the torsion of the homology groups. So I was just wondering if you have thought about this, or just
yeah, I believe this is all over the reals, but I'm pretty sure this is all over the reals.
Okay, thanks.
Okay, so now here is a step that we physicists may not have too much intuition, but there is a exact sequence that helps you calculate this relative. These are called relative cohomology groups. It's here. So this exact sequence goes as follows. And you have H0 of MGN. This can be found in Wikipedia. In fact, this is a sequence of relative cohomologies, rather famous. That doesn't mean it's familiar to us, but MGN, this is the MGN, MGN to H1 of okay, it's an exact sequence that has this term that we cared about, that we wanted to be 0 in between two other terms. The term H0, that should not have parenthesis, H0, the first cohomology group, the 0th cohomology group. So here comes, and this is an exact sequence. The exact sequence, you can read it in Wikipedia. It's very simple, some discussion, and Hatcher also has it. So here comes a powerful result from math, again, that I only have some partial intuition on it, that except, and it's very curious, that for Gn equals 0, 4, everything works quite nicely, except for Gn 0, 4. So in fact, the claim is that it's relatively, maybe somewhat intuitive, is that this set of noded surfaces, MGN modulo MGN, these are the noded surfaces, except for Gn equals 0. These are all is a connected set. So this is, they say that the noded surfaces, once you go beyond 0, 4, these are all connected. And it kind of, it's clear, I think, if this is a claim in the math literature, and suppose you have here a noded surface. So it's a node here. Oops, I want to do it a little different. I'm sorry. Oops. Why does it do that? Here is a noded surface. Maybe some punctures here, a node. Then you can keep this node here and node, make a node here. Make a second node. And similarly, you can open up this node. So then you have, for example, so you open up this node, but keep this, and there you have two very different looking noded surfaces are continuously passing to each other. I don't know how much more one needs to explain for doing this, but it's definitely a connected set, and as such, H0, the zeroth cohomology group, vanishes. H0 of this MGN is equal to 0. So we have here one good thing, which is that this term, I'm sorry, this term vanishes except for 0, 4. And actually, the term that I have less intuition, but it's also true, is that H1 of MGN hat also vanishes for GN different from 0, 4. So actually, the two sides of this exact sequence vanish for G for different than N4, 0, 4. And therefore, the group that we were interested in vanishes there. And that was the group that was this, and we were all in good shape. So it's kind of interesting that this happens, but in any case, it does, and we're left, in fact, for the only case that has to be analyzed is the homology of the space here for G equals 0 and N equal 4, which is 0G, N equal 4 is H1. The only case we need to really worry about is H1 of M04, which is actually different from 0, and it's a possible obstruction that we physicists kind of understand quite well. So what is M04? You have a punctured sphere, and you have 4 vertex operators, 4 punctures. You fix 3 at 0, 1 at infinity, and the sphere is the moduli space, the position of the 4th puncture. There are degenerations when you hit any one of them. So this moduli space is a sphere, S2, or people like to call CP1 minus the point 0, 1, and infinity. that correspond to the collisions. So here it is, point 1, 0, and infinity. This is not an 8, it's infinity. And once we have these 3 points, 0, 1, and infinity, we realize that H1 of M04, first homology, is spanned by 2 elements. And these are, if you wish, here you have 1, 0, and infinity, 1, 0 at infinity. And then these are supposed to be one-dimensional chains that are have no boundary, so closed curves that have no boundary, and they're not the boundary of something. And I think we more or less know, and this I think seemed to be what Ashok was asking. One element of the homology is a curve going here around this puncture. It cannot be, it's not the boundary of something because there are holes in the space here. It's not the boundary of whatever is outside the curve because of that. And then the other element is this one, for example. Could have, I'm sorry, it could have been taken around infinity, but you can take this. And if you add 2 of these cycles, these are cycles because have 0 boundary, they could be corresponding to one cycle that goes around the puncture at infinity. So here you have a case where there's a obstruction, there's a homology class that is non-zero, and you could be killed. But you know, we've been doing this for a while, and we kind of know what it is. It is, in fact, something that the symmetry condition, the permutation of the 4 punctures, solves the problem, in fact. So this, if you think of these 2 cycles, they form a 2-dimensional representation of the permutation group of 4 objects, some representation. Now, to have an obstruction, there should be a permutation invariant representation. So it should be a trivial representation of S4, of the permutation group on 4 elements. So you're looking for something that doesn't transform under S4. Well, if it doesn't transform under S4, it should not transform under S3, which is the subgroup of S4 where you permute 3 of the punctures. Here, the 0, 1, and infinity. So it should be a class that is invariant under the permutation of these 3 elements. But these 2 cycles here form an irreducible 2-dimensional representation of the permutation group of 3 objects. So there's no space for this thing. In fact, if you think of the intuition, is that there's no trivial representation of the permutation group here possible. In fact, if you maybe think alternatively about it this way, with 0, 1, 0, and infinity, to have a cycle that is invariant under the action of the permutation group, you would have these 3 things. But they cancel each other. This 1, 2, and 3, 1 and 2 is homologous to this thing. The sum of this thing is the boundary. It's a trivial cycle because it's the boundary of, if you wish, let me see, very big. Yeah, it's the boundary of this thing, this whole cycle. So the permutation invariant cycle is trivial. So therefore, this H1 of M04 over S4 is equal to 0, and therefore there's no abstraction. So having shown that the only case where the general argument of the exact sequence fails is also not problematic, shows that the homology groups are always 0, and therefore there's no abstraction, and therefore you can always solve for string vertices, and string vertices should exist. So my aim here was to just give us as much intuition as I have. I'm sure there's people that could have more intuition, and maybe one could do it even better in presenting it. But I'll stop here with this discussion, and I've finished, therefore, what would be the first part of the talk, and I'll move on to hyperbolic geometry.
Yeah, Barton, I have a general question,
Yes.
which is that these new GNs never go near the boundary, right?
This what?
The vertices never go near the boundary.
Right.
So given this, it seems surprising that you actually have to do a compactification to give this proof, right? Because it shouldn't matter what you do at the boundary for these or
well, I have that's true. So you could say that. So let me say two things that are a little just all what I know and a little bit contradictory. So when you try to deal with homology of non-compact spaces like this one, I think this is an auxiliary way of doing it, and presumably, so this thing. And presumably, you may be able to get to do this without choosing the particular Deligne-Mumford compactification. So this is just, I think, some way of doing this computation of this that doesn't require a compactification. So this should be well defined by itself, and the issue is just how to compute it. So I agree with you, and maybe there's a way to just do this without going through some of this calculation. On the other hand, somehow there's one aspect of another proof that we had in this paper is that you produce the Feynman region, for this moduli spaces, and let me this FGN by doing the new GN and adding the regions with one Feynman diagram, with two Feynman diagrams. And part of the arguments that are done to produce this is that you must have that if the vertices satisfy the recursion relation, this gives you a full cover of the moduli space. And there must be a rigorous proof of that. One important part of this is to show that the boundary of FGN is equal to 0. And part of that proof is, well, the Feynman diagrams, nu GN connect nicely to the one propagator Feynman diagrams, they connect nicely to the two propagator Feynman diagrams, but there's also boundaries in principle from the degenerations of the surfaces. Now, I think the pretty thing of this compactification is that these are no boundaries. There are no boundaries that you get from there. because when you get a noded surface, you sort of lose 2 dimensions. The propagator has gone to 0, but by the time the surface is noded, the way I think these people think about it, you don't have the twist angle. The twist angle also disappears. So each time you go to the compactification, you lose 2 dimensions, and therefore you don't have a boundary. There's no boundary there. So I have not a very complete picture of what's happening, but perhaps the compactification is useful to prove some other things about the Feynman rules that follow from this theory in the sense of propagators will cover the moduli space correctly at the end of the day. So
yeah, I'm wondering maybe that just to show the existence of the vortex, all you need to show is that the right-hand side is a trivial element of the homology, right?
Right.
Even if the actual homology group is non-trivial.
Yes, that's right.
Yeah.
Even
and
if
we are trying to prove too much, right? That instead of trying to show that the actual the whole homology group vanishes, maybe it's easier, or maybe it will not require compactification if you just try to prove that the right-hand side is a trivial element anyway.
Right, right. So yeah, basically, you need not show that the homology vanishes necessarily, but you need to show that that element is a trivial element of the homology. That's true. Maybe that I think it's worth for us physicists to try to understand this even more intuitively. A little bit of that happened in that the homology of the 4-puncture sphere was non-zero, but nevertheless the restriction of symmetry made it a trivial element.
I see. Okay.
In that, when you see the boundary, indeed, if you remember, I think a bit of what happened there is that the boundary of nu 04 is 3 diagrams. Is that right? It's in fact the boundary of nu 04 is what Olaf was doing, the Jacobiator, three terms. These are the surfaces that you get from S channel, T channel, and U channel, and you produce these 3 cycles. But these 3 cycles, there's something in between. So indeed, there's a non-trivial homology for the M04 or nu 04, but the thing that you get is such that it's 0 in the symmetric case.
I see.
So I think it might be that there's a direct argument that at this level studies those surfaces on the right-hand side and concludes that that must be a trivial element. So yeah, that would be actually nice.
Okay. Thank you.
Thank you. Other questions before we pass to leave this subject? It's a nice subject because I think we physicists struggled for many years trying to see, well, do they exist? Do they don't exist? Exist with this assumption, that assumption? We just and now if mathematicians give us some precise proof, then we can pick it apart and gain some nice intuition. All right.
I'm wondering, how does the mapping class group fit into this story? I mean, there was also a question in the chat. How does a mapping class group fit into the story? I mean, how much of this story goes through for take?
Well, it just built in from the beginning. You know, we built it in from the beginning, actually. I never had to worry about it. I started talking about MGN, which is the moduli space of Riemann surfaces, which is the Teichmuller space divided by the mapping class group. So I will have a little bit more to say about it, but Fenchel-Nielsen coordinates give nice construction of Teichmüller spaces, and then you have to divide by the mapping class group. But in the discussion that I had, I started with the moduli space. This is not
yes,
the
but I was wondering, I mean, the homology and co-homology groups you're referring to, are they all trivial for the Teichmüller space, for example? Is it all, are these non-trivial aspects solely due to the mapping class group? Is this the kind of thing I haven't, kind of question?
Well, I doubt it is that trivial. I actually don't know.
I mean, the reason why I'm asking is because the Teichmüller space is homomorphic to some product of the complex plane, some product of the real line, a tensor product of the real line. Okay. So, which I guess is topologically trivial. So it seems to me that the non-trivial aspect of these cohomology groups comes down to the mapping class group, but I don't know if that's why I'm not sure.
Okay.
I don't know if you have any comments.
No, I don't know. I would be surprised if the Teichmüller spaces are that trivial that they have no homologies. But I don't know. It's a question that maybe some mathematician could clarify very quickly for us.
Okay. Thanks.
All right. So let's move on to some aspects of hyperbolic geometry. So this is lecture 2, but given this schedule, I will still write it as lecture 2. So hyperbolic geometry means that you're working with surfaces with curvature equal -1, Gaussian curvature. There's a factor of 2 between K and R being the scalar curvature. I never remember which one is which. But mathematicians always work with a Gaussian curvature, which is proportional to the curvature, and it's with -1. So when you deal with Riemann surfaces, you can ask if you have a surface with punctures, so a 3-puncture sphere, how does a surface with 3 punctures looks when you put a metric of constant negative curvature? Well, it's a complete metric in that the puncture is a removed point, a single point that has removed, and every geodesic that goes to the puncture, to that missing point, has infinite length. It's actually the way this surface looks is some sort of cuspy. I'm not doing a very good job. It's a cusp, like 3 cusps. Here is P1, P2, and P3. So this is how this metric kind of looks. It looks more symmetric, more beautiful, if you wish. Looks very symmetric. There's no moduli space. It's just a 3-puncture sphere, 3 local coordinates like that. And now, remember, our task was to draw curves around the punctures. So we should draw 3 closed curves around the punctures. And we should do it in a nice way, maybe using hyperbolic geometry to draw them. And well, draw 3 curves. And the best you can do is draw them like this on the surface. And these curves are, if you take them in some sense, the most symmetric curves that you can write are called horocycles. And they're not geodesics. As you can see, they can be slid off to the punctures. The puncture is at an infinite distance, so this is just a sketch. Would take an infinite iPad to draw them correctly, but the area is going down to 0. This is a finite area surface by the Gauss-Bonnet theorem. And but these drawing curves are not geodesics. Now, this is the approach used by Pius and Musavian, and they use these surfaces to try to build a solution of the geometric master equation. And it's a clear natural choice in some case, but it's difficult to work with because remember, we're supposed to amputate those local disks and glue together surfaces. And if you glue two hyperbolic metrics with across curves that are not geodesics, you don't get a hyperbolic metric. You get a curvature singularity at the seam where you've glued them. So this makes the determination of the higher vertices difficult because you have to abandon the hyperbolic metric, and but it's still doable in an approximation scheme where you take these horocycles to be small, and you get the results of Pius and Musavian. I think a lot of the contribution that they did was to try to explain some other parts of the hyperbolic string field theory, in which they try to study, for example, the measure on this moduli space in terms of Nielsen-Fenchel coordinates, Fenchel-Nielsen coordinates. They found some expressions, and they tried to explain how results such as mathematicians like Bisarcani, Shane, and others that learned how to do integrals over moduli spaces of hyperbolic metrics, starting from Teichmüller spaces, how we could use those in string theory. And they painted a picture where it would seem plausible that some computations that are forbiddingly difficult may be doable. So, on the other hand, these vertices are not quite optimal, and what we're going to be trying to do is to replace this by surfaces with boundaries. Now, it's not obvious how to do that, but if you have a sphere with 3 boundaries, if you wish to, this sphere, let's do this, this sphere here, with the 3 cut holes, in hyperbolic geometry actually has a nice construction in which there's a unique hyperbolic metric in which the surface looks like this. It's called the Pan's diagram, and these boundaries are geodesics. So this is more promising because you can glue surfaces across geodesics and you remain hyperbolic. And in fact, this gluing of surfaces in this way with Pan's diagram is the Fenchel-Nielsen construction of Riemann surfaces, in particular Teichmüller spaces. So this is maybe a good beginning, and that's the approach we took. In fact, you know, the main idea is really due to Costello in a conference where we were both attending. He said that instead of the Caspi construction, he would favor a construction with geodesic boundaries. And he believed that that should give a solution of the master equation. And indeed, we wrote together the details of why this works. And there's some surprises, but overall, basically, the original idea was just very good. So, so consider surfaces. Let me say a little bit more about these surfaces. So surfaces, first of genus G, S of genus G. Now, this is not a Riemann surface to begin with. It's a two-dimensional surface, and you don't fix anything about the surface. It's just topologically a two-dimensional surface, topologically, with genus G. Then you try putting different metrics on it, and you define the so-called Teichmuller space of hyperbolic metrics on S. This is the Teichmuller space of hyperbolic metrics on S. And there's no punctures yet. So you think of the topological surface and you put different metrics. Metrics in which the surface is big, is little, is tilted, goes in different directions. So you can put many hyperbolic metrics. The uniformization theorem of Riemannian geometry of Riemann surfaces says that these hyperbolic metrics are in one-to-one correspondence with the complex structures on that topological surface. So the space of Riemann surfaces on this topology of genus G is the same as the space of hyperbolic metrics on S. So that's why hyperbolic metrics are useful. Two different hyperbolic metrics are two different complex structures. Now consider again these surfaces, this S of genus G with n boundaries. So in this moment, we'll consider, now it's not n punctures, it's n boundaries. The Teichmuller space of genus G, n boundaries S, and this is the Teichmuller space of hyperbolic metrics, with just saying one more clause, with geodesic boundaries. So you put just the requirement of geodesic boundaries. And now you say, well, that's okay, but this is not what we want. We want surfaces with punctures, not with boundaries. Surfaces with boundaries have more moduli than surfaces with punctures. Indeed, if you had a three-hole sphere again, three-hole sphere, and we have it here. If you try to put all kind of hyperbolic metrics, in fact, the hyperbolic metrics are classified by showing the final form of the surface, which actually has three parameters, L1, L2, and L3. These are geodesic boundaries, and these are the lengths of the geodesic boundaries. So this three-hole sphere has three moduli parameter by the uniformization theorem. When you try to put hyperbolic metrics, you figure out that once you fix L1, L2, and L3, you get a unique metric. So those parameters are parameters of the metric, and these are the space of conformal structures on a sphere with three holes. It has three real modular parameters. This is something that if you've worked with string field theory or thought about moduli spaces, it's kind of familiar. You think of a sphere and then put finite tubes, and the length of the tube could be the length, the three length parameters. Or you think once you have a metric, you cut the hole in the size of the hole, but it's a true fact. These are three moduli parameters, the three lengths. Now, on the other hand, if you think about this, we were thinking of nu zero. Yes.
It will be the end of this hour.
Okay, we're almost there. Okay, so let me, I don't know, I think it might be a good place to stop, but I want to say maybe 2 minutes and quit.
Yeah, thanks.
So I want to give the main ideas, and we're going to need a theorem in order to make this clear, but that is a precise result. How can we relate this to the vertex, the nu 0, 3? And this was, again, part of all difficulties in doing hyperbolic geometry. People say, okay, let's use as a string vertex the Pans diagram. But then what should you choose for L1, L2, and L3? There's several parameters. You should choose one. But then, okay, what are we going to do with that one? Indeed, you should choose one. So because the dimension of M03 is 0. So we need just one string vertex. And here, in this moduli space, you do have 3 real parameters. So this moduli space is not quite right. So you should work with the moduli space T, G, N, L of S, this Teichmüller space of hyperbolic metrics and boundaries of length L. So if you fix the boundaries, all of them of length L, you eliminate those extra parameters, and in fact, you now get that the dimension of this space is really the dimension of MGA. You don't get more dimension once you fix the size of the boundaries. They're the same, but there are more powerful results happening that are going to allow us to do this construction. At this point, let's stop here. We'll have to solve the problem of we don't want boundaries, we want punctures, and then we need to relate these surfaces with boundaries to moduli spaces of surfaces with punctures. So these are the challenges in this thing. One surprising thing that will happen is that the value of L must be smaller than a certain amount in order for the theory to work, for the string field theory, but we will see all that in our third lecture. So I'll stop here. Thank you very much for your attention.
Thanks a lot, Barton. So we have a small break for 10 minutes, and then we reconvene and have the question and session for Olaf first, and then for Barton. So we see in 10 minutes.
For example, you talked about grading, okay, but when you have, for example, both differential form and fermionic grading, they do not mix. So you have you to consider a big grading or what else?
I'm not entirely sure I understood the question, but I guess the issue perhaps the issue you're alluding to is what happens if you have fermionic on bosonic fields, or if you consider supersymmetry more general, I mean, more specifically, then you have an extra grading that is not part of the grading. Well, actually, I haven't really discussed the field theory dictionary yet, so I will come to that tomorrow in the next lecture. But there you have a space of fields, you have a space of gauge parameters, you have a space of field equations, and then possibly higher spaces. So in the space of fields, you just put everything together, bosonic and fermionic fields. So you could have further gradings, you could have further structure. So sort of a subgrading of that space. Well, that's just a comment. I'm not sure if that's actually related to your question or not. But,
no, it's that. I was asking whether you can have multiple gradings according to what you are interested in. If you have forms, you have You have a kind of grading. If you have fermionic degrees of freedom, you have a different grading. This is,
yes, yes.
Okay.
Yeah.
They work
sure.
Independently. Okay.
Right. You can have multi-gradings. That's very true. Yes. And then, of course, then you can ask all kinds of fun questions like, I mean, a natural thing to look at is if you consider differential forms that don't take values just in a Lie algebra, but take themselves values in a higher algebra, like in L-infinity algebra, then you have a higher grading, or so you have a Z2 grading. You have a grading according to differential form and to the L-infinity algebra. And then you can ask, what is that? Does this larger space also itself have an L-infinity algebra interpretation? And then that's a little confusing. The first thing you have to settle then, what is the right grading on this bigger space? And I believe the correct answer is there is an L-infinity structure, but with respect to a sort of diagonal grading along this two-dimensional grid.
Okay, perfect. Thanks.
Hi, I have a question. So well, when you had defined L-infinity morphisms, you had said something about an intrinsic degree of the function f. Could you explain what that intrinsic degree means? I did not quite get that.
Oh, yes. Thanks for the question. So the intrinsic degree also existed already for the L-infinity brackets. So it just means that if you have any kind of function with a certain number of inputs, the degree of the output is given by the sum of the degrees of the inputs plus the intrinsic degree. So the L-infinity morphism have intrinsic degree 0, which just means that's just the sum. The L-infinity brackets in my convention had intrinsic degree -1, which or you can also pick +1. That's just what I meant. Sorry.
Oh, all right. Okay. Yeah. Thank you so much. Thank you.
Olaf, you spoke of morphisms. Is there like definition of isomorphisms? Do you care? Is that something relevant?
Well, usually I think my understanding is mathematicians, who are the people who come up with these definitions, they don't care because the natural framework in which to think of L-infinity algebras or A-infinity and all these things is it's really when it comes to homotopy equivalence. So like you were saying, when you and that's of course what I will discuss tomorrow, when you map between different spaces, you have an L-infinity morphism. If you have as a special case, if you have a homotopy equivalence, so where this the linear part of the map may not be invertible. Okay. Now you can define an isomorphism by saying so the short answer is there's a natural notion of isomorphism, which is when the linear part is actually invertible. So you can go in both directions. So you have so going from x to x prime, there is a map, and there's a map from x prime to x, so that this is really the identities in both directions, not just in one direction, in both directions, which is a much stronger concept than the homotopy equivalence we really care about, where you have only in one direction that is composes to the identity, not in the other direction. And then and that's really the case where all these structures become powerful. So because it's like if you have a Lie algebra, the natural notion of isomorphism is or the natural notion of equivalence is really that of an isomorphism, right? You have two seemingly different Lie algebras are equivalent if there's an isomorphism between the vector spaces, so that the brackets on one are just mapped directly to the brackets on the other. And that's a very boring notion. It just means that you have literally the same Lie algebras written in slightly different bases, right? It's it's the same vector space, but you've labeled the objects slightly differently. So it's a boring concept. While in L infinity, I think it's a much more intriguing concept, because there you really can go from spaces of a certain size to space of a very different size, right? I'm not sure if that summary in words does justice to the intuition that people have, but that's sort of how I seem to understand it.
So the vector spaces are not isomorphic necessarily.
No, no, absolutely not. Yeah. More questions?
Just a question about the philosophy. You used derivative, product, and so on. And
yes.
The reason essentially is that you are thinking of string vertices, which can be thought as maps, because maps from Hilbert space to different Hilbert space when you merge them, or which is the reason why you use the derivative and co-product instead of
so that's really, that's not my decision. That's, I think, how mathematicians prefer to think about it, because the basic building blocks are really these L infinity maps that introduce the B1, B2, B3, B4. Now the question is, how can you make these maps into something bigger, where you have a single condition that gives all the L infinity relation that's squared to 0, and that is really that object is a co-derivation, because you have to give meaning to sort of adding them up. Now there is a dual interpretation is in terms of a derivation, and that's really then more closely related to the BV formalism, where you reconstruct the L infinity maps from the Taylor coefficients of what's called a homological vector space, so vector field. So that's a vector field on the BV manifold that squares to 0, and you can start Taylor expanding, and that sort of gives you the structure constants of the L infinity brackets. And if you impose the condition that squares to 0 and write it out, you find that this gives you precisely the L infinity relations sort of written out of these structure constants. So in that sense, you can absolutely encode the L infinity relations in terms of a derivation rather than a co-derivation, meaning a vector field, which is a derivation. But it seems to me that this is intrinsically sort of coordinate or basis dependent, the way to do it. At least I have not seen a natural way to just do it in a basis independent way. And I think that's the reason why mathematicians prefer the co-algebra and co-derivation picture, because there you just can take directly those maps, add them up, and give a meaning to that expression. And you never have to specify sort of something like structure constants to build some Taylor coefficients and things like that. So I think it's the co-algebra picture is more natural for this purpose.
Okay.
I don't know if any of the experts in the audience wants to object to that summary, then please speak up.
Because I was looking to what is called the free differential algebra, which was used in supergravity, which is essentially the dual formulation of, at least in a mild sense, of this, where you use the differential, the usual differential, and you have not only one form, but you have higher forms, and so you can build it's a kind of a generalization of Maurer-Cartan, let us say this way. It's a Maurer-Cartan with higher forms.
Yeah.
And since this, what you're
writing down is essentially a generalization of Maurer-Cartan with higher forms. I was just wondering the reason why it was not possible to formulate using what a kind of free differential algebra. This is all.
Yeah, I think so. In free differential algebras, you still have forms, normal P forms, and the Rahm differential, or not? Or
oh yes, they have P forms, the Rahm differential, and so on.
Yeah, yeah.
And but you
never actually use that. So there's sort of a tiny but important extra step involved, where just let's forget about that. This is actually the Rahm differential, and you have forms that you can wedge together, etc. Just let's just use the relations, and then you can do I think more general things. So so as I will illustrate tomorrow, in normal field theory with a second order kinetic operator, you normally not think of in that language, because you have sort of this picture in your head that D is like the de Rahm differential, so it's a first order differential operator. But that doesn't need not to be the case. So if you think of Young-Mills theory, where you have a second order kinetic operator, of course, that is part of an L-infinity algebra, as I will explain. And it's just the abstract differential that defines the chain complex. On one space, it's the second order differential operator that is given by the free action. And in another space, it's just given by a first order differential operator that defines the gauge transformations. And that the squares to zero just means that the composition is zero. And that is true by gauge invariance.
Okay, thanks.
Can I ask a question as well? I was wondering, how does OP associativity, how is it encoded in the L-infinity relations, if at all? And the kind of OP associativity that one has from on the world sheet, for example. I don't know if that, maybe it's a naive question, I don't know.
So which associativity? I mean, general associativity is relaxed.
In the world sheet sense. I'm trying to understand, to link what you said to the kind of structure.
Well, I mean, so maybe these things will become clearer when we look to actual examples tomorrow. But it's, so if you, so the very first example I will discuss is just a but a scalar field without any gauge symmetries. And there, the two brackets that defines the cubic vertex, if you have one, is just defined in terms of the normal products of two scalar fields. So that product, of course, that you use to define that bracket by itself is associative, because it's just a normal product. But the point is that if you check the Jacobi type identities in L-infinity language, you always have to sort of insert the appropriate brackets themselves. And at that level,
does that encode the OP associativity of in the CFT of the well sheet sense?
Well, the question is what you want to do with the world sheet. So far, there's nothing here specific about string field theory or string theory.
Yes,
so
I've just encoded in that structure. Or it's something.
Well, I don't know. So
for example, the OP of if you have three vertex operator insertions in the world sheet sense, and you first compute the contractions of the first two, and then the result of that with the third, and then you can do it the other way around, compute the contractions of the second and third, and then compute the result of that with the first. Is that so? These two ways of carrying out the computation should be the same. Is that somehow encoded? That's what I was.
Well, I mean, the point is that you have to discuss that in the context of a field theory that you want to describe in an L-infinity algebra.
Yes, something.
So do you want to encode the two-dimensional world sheet theory as an L-infinity algebra, or you want to use that to define a target space string field theory?
In the string field theory sense.
Okay. I'm not sure what the direct. I'm not sure what the direct L-infinity translation of that is on the top of my head. Maybe probably Barton knows, or some of the other experts.
So how does a string field then? I mean, you discussed about these vector spaces, but how does, for example, one see a string field? Just to connect to some.
Sorry, what was the question about the vector spaces?
So you spoke about these vector spaces in fairly sort of mathematical formal terms. I'm just wondering what the relation is. What is a string? Where is the string field, for example, if you want to think in terms of
so the string field lives in one of the vector spaces of this that defines the L-infinity algebra. So we have this integer graded space. As I will explain tomorrow, there's the space at degree 0 in some convention should be thought of as the space of fields, and that's where the string field lives.
Okay.
If you specialize to string field theory, yeah.
Okay, that makes it clearer.
I don't know if I can add something, but so I think Olaf has more or less said, if you're talking about vertex operators, that's not the way the L-infinity would enter for writing the two-dimensional conformal field theory. The two-dimensional conformal field theory, or the field theories you write with L-infinity, must have a set of fields. So for example, you have free bosons, so the fields are the x's. And that's it. The vertex operators are not relevant to the writing of the free boson field theory, which is kind of trivial. So the L-infinity is not helpful to construct the conformal field theory. So when you mention vertex operators, which are composite operators of the two-dimensional field theory, the associativity of OPEs gives constraints on the properties of the three-string vertex, and those somehow must be consistent with the axiomatics of the three-string vertex. But I don't think there's much more to that.
Because I'm thinking of it as a vertex operator as just a basis for your string field.
Right, the vertex operators are a basis for the string field. So in some sense, whatever you assign, so if you were doing, in fact, in some sense, the associativity of the OPE has to do with 4-point functions in some sense, because you're trying like three vertex operators, and you expand them by OPEs, and they give you another vertex operator, which is the total thing. So in some sense, this is some conditions between the 4 product and the 3 product. So I don't think
that's encoded in the L-infinity relations.
I think it's sort of implicit in there, but I don't think it has been clarified too much, because in the OPEs, you sort of let points collide, and you let sometimes points approach. So the way how this is related to a 4-string vertex is not all that clear. But I think Sonoda was one of the few people that have said that the associativity, the consistency conditions on the conformal field theory are based on the associativity of the OPEs and one more modular invariance. And he's the closest that has been to that stuff. But I wanted to make just one other comment. Olaf mentioned vector fields, why people like co-derivations more than vector fields. I think some people, yeah, I think that's
some people not.
Yeah, it depends what you do. From the Batalin-Vilkovisky viewpoint, the vector field is a little more natural. I believe, because there's something in symplectic geometry, something called Hamiltonian vector fields. If you have a function, you take a derivative with respect to the coordinate that gives you an object with a lower index, and then you use the symplectic form to raise the index. So it's a natural construction from functions to vector fields. So the vector field that squares to 0 in BV is just the vector field corresponding to the master action. So given the master action, there's a vector field by the symplectic geometry, and that vector field is the one that squares to 0. So at least in BV, it's kind of natural going that way. It's just a comment.
May I ask a question?
Sure.
So two questions actually. One is that if I understood correctly, you said that if B3 onwards, all these brackets are 0, then you'd get a graded Lie algebra. Is that correct?
That's correct, yes. Differential graded Lie algebra.
Yeah, okay, differential graded Lie algebra. So the question is, are there examples where you have some finite number of Bn's which are 0, but you still have a whole L infinity structure, or is it necessary for all of them to be?
Yes, so most examples are like that. So for instance, if you write Young-Mills theory in standard form, this corresponds to a genuine L infinity algebra with higher brackets, which comes from the fact that you have a quartic vertex. So under the dictionary, which I will explain tomorrow, that corresponds to a 3 bracket. So you have a 3 bracket that's non-zero, that is there. And so it's a real genuine L infinity algebra.
No, I guess that is not what I asked. What I was asking is that could you have an L infinity algebra where you have some of the Bn's which are 0, a finite number of Bn's which are 0? I mean, there's no 3 vertex, but a 4 vertex, but again, no 5 vertex, but a 6 vertex, that kind of thing.
Yes, I mean, well, I mean, I'm not sure if there's a natural theory you can write down with that property, but I mean, it's, let's put it that way. If you write down a field theory with that property, I can give you the corresponding L infinity algebra.
Mm-hmm. The second question.
I'm not sure if you have something more specific in mind. But,
no, I was just wondering as you know, just curiosity.
Olaf?
Sorry?
I mean, if you have a 5-4 theory, which has a 5 goes to minus 5 symmetry, does that have this kind of structure?
Sorry, your connection is not very good. I couldn't quite understand. Yeah. Can you try again?
I'm asking if you have a 5-4 theory.
Yeah.
Which has a 5 goes to minus 5 symmetry.
Oh, you mean you don't have a cubic term then? Yes, yes. Yeah, that's of course. So yeah, that would be a trivial example where you have a 4 bracket. You have a 3 bracket, which gives you the quartic term, phi to the 4th. But if you leave out the phi cube, let's say by imposing a symmetry, then that corresponding 2 bracket is not there. So it's actually 0. Yes. So that indeed. So that would be an example where you have a differential.
But Ashok, in this case, all the other higher Bn's will vanish, right? Or that's not the case?
Well, you can keep adding more non-polynomial terms, right?
Okay, but you still keep a symmetry which will forbid all the odd vertices then. Okay.
Yeah.
Okay, thanks. I understand. Now, the other question is that I think it's also related to what Barton was asking about morphism. Is it possible to do some kind of field redefinition which will give normal differential graded Lie algebra the structure of a L infinity algebra with all non-zero bn's, but in that case, I guess there's some kind of this morphism that you talked about, which will actually make that a trivial example. Is that correct?
Right, that's a good point. So of course, in normal field theory, you can just take, let's say, a cubic theory, which corresponds to a differential graded Lie algebra, so only two brackets, and then you do a horribly complicated field redefinition that makes it look very potentially non-polynomial, and that would correspond to an L infinity morphism from a DGLA to an L infinity algebra. That's much more complicated, but it would be an actual. If it's a field redefinition, it means an invertible, right? So I think you would actually call this an isomorphism. The more interesting cases are when you actually integrate out fields to go from one to the other. So that's what happens with homotopy transfer, as I will discuss tomorrow.
Thank you very much.
Okay, so we are now at the middle of the question and answer session. So except if there is an urgent question for Olaf, I suggest we shift to question to Barton's. And in any case, tomorrow we have another question and answer session at the end of the day. So I think we can thank Olaf for the answer.
Okay, thanks to you.
Actually, I have a question for Barton.
Yes.
So you discussed about this Pearson-Mosavian paper. It's very nice work where they discuss this unfolding of moduli space and write integrals over moduli space as integrals over Teichmuller space.
Right.
And of course, I can imagine that in string perturbation theory, that's very useful because Teichmuller spaces are very simple in a sense compared to moduli space, MGN. But I was wondering, I mean, in corresponding string field theory, I guess you want to construct integrals over new GN, the subspaces, new GN. But I can imagine that in order to do this unfolding for new GN, you have to map new GN from the MGN sort of subspace to the corresponding Teichmuller version of new GN. There'll be some new primed, which is sort of the Teichmuller, the unfolded version of new GN. And I can imagine that this might be quite complicated. I'm wondering, does it really simplify calculations? I can imagine that in string perturbation theory, it would simplify things perhaps a lot. For example, you can compute the volume of moduli space like this. But does it really help to compute the vertices, this unfolding?
Well, I think that's an open question at this moment. So indeed, there were attempts by people to try to do that. There's this mathematician Anderson that we cite in our paper trying to do recursive relations between integrals at various degrees. So you're absolutely right. The new GN has a particular challenge. So if you are looking for a closed form expression for the string action, there is a challenge there how to pass from the new GN to its image in Teichmuller space and work on it and see if there's a simple way to do it. I don't think it has been done, but I think it's a very crucial question, actually. The other possibility, of course, is that you may want to do off-shell amplitudes, and that would involve the whole integral over moduli space. So that has its own challenges, as we will see. Suppose you want to use, if you're not doing string field theory, you could use sort of the section that I will construct later. So remember MGN, PGN on top of it. Maybe I don't know if I think maybe I should share just to make a couple of comments. If I have it there, might as well. So I use this thing I was doing. So we have MGN, and you have this new GN. And what we will see tomorrow is that with hyperbolic metrics, there is a natural way of extending this section to go all the way using hyperbolic metrics. But I think it's more natural, and the way the string field theory will extend the section is different. It will extend it in some other way. And these ones don't have a very natural string field theory degeneration. When you reach the boundaries, this become more problematic. These ones become the Deligne-Mumford compactification that for some reasons they're very convenient. So the Feynman graphs construct this whole thing, while the normal rules of hyperbolic geometry construct this other one. So if you want to avoid integrating over just nu GN, and you think the whole integral is easier, you have two options. Try to do the integral over the whole sort of hyperbolic section, and do the integral over the Feynman section, which is a little different. And this is a feature of the hyperbolic string field theory that makes it different. The string field theory rather nicely does this one, but the sort of basic theorem of hyperbolic geometry does the other one. So maybe it might be possible that these ones could be computed using hyperbolic geometry all the way. This is purely hyperbolic, and the FGN in the Feynman rules of the string field theory are a mixture of hyperbolic and flat structures. So we'll.
Well, what do you mean by this? The flat? How does the flat structures come into play?
By the time you work out the if you want to assign metrics naturally to the Feynman graphs of the hyperbolic string field theory, the most natural metrics are flat. Let me say it this way. Suppose you have a string vertex, and you have another string vertex here. Here have length L. Now, this length L, as I was hinting, is going to be kept forever fixed at value L. We're never going to change it. How do you construct the suppose you glue them, then you'll have this. Well, something like that. I'm not drawing beautifully, but gives you the picture, L. How do you construct the degenerate surfaces that correspond to a propagator in between? If you want to use hyperbolic geometry, strict hyperbolic geometry, really there's no option but to take L going to 0. So integrate over L and let a pinch be created. The reason is that the degenerate surface happens when L goes to 0. You could say, oh, why don't you put an annulus? Here is an annulus, a hyperbolic annulus. But in a hyperbolic annulus, the boundaries are not geodesics. In a hyperbolic annulus, the boundaries tend to go to the middle. So if you insert it here, if you put it in the middle, the hyperbolic annulus, the metric will not be hyperbolic. This is a geodesic.
Is that a problem? I mean, why is that a problem?
Well, that's if you want to work with hyperbolic metrics and use the tricks of the mathematicians of hyperbolic geometry, you just suddenly are outside hyperbolic geometry. So that's not very good. You know,
not a problem of principle, right? I mean, in principle, though, that's okay as well, right? I mean, it's just a technical issue that, I mean, in principle, the metric could be whatever it wants. I mean, it could have discontinuities and anything, provided the total Euler number is fixed and so on. Right?
That's true, but if you are going to rely on hyperbolic geometry to do integrals, to produce the moduli spaces and all that, you're going to lose all your technical control. So I think it is problematic in that sense. In principle, it's true. You're going to do sewing of this thing, and sewing doesn't involve metrics. But in terms of metrics, the only solution we found for this difficulty was to put a flat tube here. And this is...
that's where that flatness comes in that you were referring to before.
Exactly.
Okay.
So this surface, the metric is continuous. The first derivatives of the metric are continuous, and which fails if you put the hyperbolic annulus, and only the second derivatives are discontinuous. So this will have k equals 0 here and k equal 1. So in some sense, this corresponds to going off the hyperbolic section and going into a mixed kind of section. I will argue that there's two ways of thinking why this is very natural, and I don't know if there's room for doing better in this thing. I actually doubt it. I think k equal 0 is actually fairly natural. So these surfaces are a little funny, but they have showed up in other contexts, and will be part of what I will say tomorrow. But it's a mixed situation. You see, each time you glue across things that are, you see, if you're just purely hyperbolic, you have to admit short curves, like this ones, because if you want to be purely hyperbolic, that's how hyperbolic metrics degenerate, by producing very thin necks. That's not quite, as far as I understand, it's not quite a very tractable compactification of moduli space, but that is a little subtle, goes against, it's not, I'm pretty sure, but I'm not 100%, 99% sure, it's not a Deligne-Mumford compactification of the moduli space. So I think it's, and it's not possible in the string field theory. In the string field theory, L is fixed. So there's no way to go around it. This kind of hyperbolic metric is not going to be produced by this by a
Isn't it-
string theory, I think.
Isn't it possible though to keep L fixed and just integrate over the position of one of the external states instead?
Well, that's not, you don't quite have that freedom either, because the three-string vertex is L, L, and L. So the three lengths have to be L, and there's no moduli anymore on the pants. The pants has no moduli whatsoever. The only place where you get the moduli in the Fenchel-Nielsen is by integrating over lengths and integrating over angles. But the vertices you cannot integrate over lengths, so you suddenly can't.
So you'd have to depart from the Fenchel-Nielsen parameterization in order to do
right.
that.
But I think the Fenchel-Nielsen parameterization is nice, and the beautiful thing is that in this region, however, in this region, in the new GN region, the Fenchel-Nielsen parameterization can be used to construct those surfaces. You can design what is this thing, because this new GN is an intrinsic vertex. So if you do the new 04, for example, you will have an L, an L, an L, and an L. But now you can allow an L prime here and a theta for an angle, because you are in an elementary vertex. In an elementary vertex, the intermediate lines in between don't have to have the length condition L. So the Fenchel-Nielsen construction is useful for inside the moduli space of new GN. So yes, Fenchel-Nielsen will not do the whole section in the string field theory, but let me say it this way. The action, which just involves the new GNs, is purely hyperbolic. It is the Feynman rules that suddenly take you a little away from it.
So Barton, if you take L to be small, then mostly it's covered by the new GNs, right?
When L, the large L's are...
No, small L. These L's, the lengths.
This L over here, the external L?
Yes.
Yes.
So is it possible that somehow when you do Feynman diagrams, you calculate the hyperbolic section and then calculate the difference, because that may have been there may be more control on the difference between the Feynman graphs and the hyperbolic surfaces, right?
Right.
Because the difference is very close to degeneration.
Yes. Right. So basically, what you're saying, make the new GN bigger. Let me see. Make the new GN bigger by choosing L very small in such a way that the FGN will be just a little deviation. Is that?
Yeah, exactly.
Yeah, I think that would be a possibility. So you could think of amplitudes as the L goes to 0 limit of a purely hyperbolic string field theory.
Yeah, I presume you will still have to make some corrections because I mean divergences near the boundary of the moduli space, right?
Right.
And so those probably have to be corrected by the FGNs. But I would think that they will be controlled correction. So the difference probably will not be hard to compute.
Right. That would be nice. So yeah, the action itself will, so basically when I say that the L goes to 0 limit of the action can be made more and more accurate, and maybe for some calculations accurate enough. And,
yeah.
Right. Absolutely, I think that is correct. Yes.
Related to this, if you take the pen, okay, and you put on one hole or boundary the vacuum, do you get the propagator? Because what you could do is to sew 3 pens and then put one of the legs on the vacuum, so you would get a 4-point function.
Well, so
the question is, sew 3 pens, okay, and then you get a 5 points, okay, without a propagator, okay.
Yes.
But if you take the pens in the middle and you put a vacuum in the pens in the middle, you get something which looks like a propagator.
I see.
At least when you do not string field theory, but you do normal string theory, you could think of something like this, because when you close one hole or you saturate one leg with a vacuum, you get something like the propagators. So
I think that's more or less a 5-point function like that, and you're saying, yes, you have these L's here.
Yes, but you put the vacuum
here.
in the middle. Yes.
You close it off. A zero momentum vacuum.
Mm-hmm.
Yeah. Right. Yeah, I don't know. This is you know, it will act as a propagator, but I'm not sure how you go about building a theory this way, a string field theory this way. But
just a curiosity.
it is reasonable that yeah. Wow. Still, you know, I think the difficulty of thinking of that as a propagator is that the vertices with L fixed don't have moduli. So at this moment, since L doesn't have moduli, in the 5-point function, you should get 2 complex parameters. And the only thing you get is 2 angles here, the twist angle here and the twist angle here. But since the length cannot be changed, this diagram only has 2 parameters. And in order to think of it as a propagator, it really should have 4 parameters for a 5-point function.
Yes,
so, but
it's a 4-point function.
Okay, if you think of it as a 4-point function, it's this. You know, I still think the difficulty in this case is that you don't get the degenerations, because however theta is, you don't degenerate. And presumably only the difference of thetas here makes a difference. So you don't get enough. You know, it's closing off a pant doesn't make it into a propagator in that sense, because you still cannot control the length of the object. The object is too rigid, I think.
No, okay, it sounds reasonable. Thanks.
Yeah.
I also have a question about the pants.
Yes.
So if you are interested in string theory with including also open strings, then you might just be interested actually in the moduli space of these pants.
Yes.
If I understood you correctly, you are saying that the Teichmüller space is given by R cubed, right? Because you have one factor of R for each length of the boundaries.
Right.
So what would be the moduli space? What would be the modular group that I have to mod out? Is it just a permutation of the three boundaries, or is the modular group different?
You know, so this is the sphere with three holes, and as we said, we have three parameters: L1, L2, and L3. So does it go beyond the permutation group of the three lengths? Certainly, that is part of it. Yeah, I think it's again a very precise question you're asking, and the only right answer is a precise answer. I tend to agree with you that probably if the L's are two surfaces with different L's, there's no way you can map them to each other. So modular group.
So this is the answer to this question also depend maybe on the fact, I mean, what kind of deep range these boundaries are ending on, or do I always have to mod out the permutation group?
I don't think it depends on that. Let me say, of course, that the open closed string field theory has more elementary vertices. This Min-Jae Cho from Harvard wrote a paper on that. So writing the vertices, the hyperbolic vertices for the open closed string field theory. But I think nobody has analyzed precisely this thing. I was going to say that if I do the closed string field theory sort of picture of this, I sort of probably can map out the moduli space because it's low dimension enough. If you take a Witten vertex and you have three stubs, so these are three stubs of the closed string vertex. This is kind of the analog. So these are H1, H2, and H3, the heights of this thing. These are circumference 2 pi, for example, with three boundaries. So here you see three moduli parameters. And as long as you have these things, these are three modular parameters. Now, since the punctures are supposed to be distinguishable, I actually don't think you have to divide by them. You know, the moduli space must include all the permutations of these things, but I don't think a division is really necessary. The punctures must be, you know, there's a difference whether you consider identical punctures or different punctures. So in string field theory, we usually think of different labeled punctures. So I don't think you even have to divide by these things. Now,
I mean, also in the case that you really have boundaries and you consider open strings, I mean.
Right. Yeah, in this case, yeah, I think my impression is you don't have to really divide here. It is like the moduli space of M04 or some people draw it like this, and region 1, region 2, and region 3, the whole plane. And it's the whole thing, but the permutation group of the punctures moves the region 1 to region 2 to region 3. But the modular space is the whole thing. You don't need to divide it because the punctures are supposed to be labeled punctures. So I probably, I'm not sure, but your question is good. I'm not sure here.
Actually, a related question, which might even be simpler, is what is the mapping class group of the n-punctured sphere? So instead of having this finite radius L's, just
well,
if you just take the L's to 0, what would be the mapping class group of that? Is it just a permutation? Is it something more complicated?
No, you know, the modular space of the n-puncture sphere is kind of simple: 0, 1, and infinity, and then you have n points: z1, z2, up to n minus 3 points. And the modular space is the whole region of this complex values. So
so you're saying basically that it's equivalent to the Teichmuller space of this.
Yeah, I don't see what is the Teichmuller
space. So
space.
you're saying T0n is equal to M0n. Is that what you're saying? Only for sufficiently large n.
No, it's not necessarily true. Let me. There is some mod. Yeah. Okay.
Normally, string field theory vortex has a 1 over n factorial, right? That takes care of the division. And then when you put different external states in different legs, the n factorial just goes away.
Right.
So it really is just a permutation group of n points, the mapping class group.
Yeah.
Okay, that's very interesting.
I thought the 1 over n factorial basically takes into account that fact, right?
Okay.
Okay. Right. And now, what I remember from discussions of people, they've told me that if you choose, so this may or may not be the case, but I think it was explained to me that if you take, for example, one paradigm L1, L2, L3, L4 fixed, and you do a Fenchel-Nielsen construction. So you must have L and theta, and L from 0 to infinity, and theta from minus infinity to infinity. Fenchel-Nielsen does that. They include thetas that go beyond this thing. And then apparently this goes into M04 in many complicated ways. So overproduces M04. But the theorem about Teichmuller space is that you choose a graph, you just choose one pan decomposition, and then just use all these internal geodesics that you have there with the pan decomposition and integrate over L and theta, and this thing will produce the modular space infinitely many times. You know, that is familiar, I think, in the upper half plane for the tori. You know, the usual strip that you get from minus pi to pi, the integral over the twist angle, goes to the whole complex plane. And that becomes one of the disconnected diffeomorphisms. So there's a large Teichmuller space of the sphere, and presumably the action of the mapping class group in here, in order to understand it, is a little complicated. But you produce
this due to the finite size L1 to L4? Is it due to the finiteness? Is this due to the finiteness of L1 to L4, or would it still be produced infinitely many times if we took L1 to L4 to 0?
If I'm sorry,
I mean, this overcountedness, the overcounting that you're referring to, the fact that M04 will not be equal to T04, this is what you're saying, right? If I understood correctly.
Yeah, that's right. It's completely different from T04.
So is that due to the finite size L1, L2, L3, L4? Or is this still true when you take the L's to 0, the external L's to 0?
Yeah, I think it's the same. So, you know, one picture, so you always have to find, if you're talking with a sphere of, if you want to go to the moduli space without boundaries, you know, you could work, then you must turn the boundaries into punctures. So one way is to add infinite cylinders. There are other ways, and you could figure out the moduli space. Well, you need some way to turn them into punctures in order to compare. So I think the claim is that any natural way of turning this into punctures, and when you integrate from L equal, you know, it's clear. You see, the thing that is clear is that you're going to get infinitely many times M04, because theta is going to go from 0 to 2 pi, 0 to 2 pi, and I think it's intuitively clear that that doesn't change the surface.
Yeah. If you just constrain theta from 0 to 2 pi,
apparently that doesn't quite work. For some reason, you see, the other thing that is not completely clear is where the other degenerations will happen. So how do you get, here you can see that when L goes to 0, you get L1 and L2 separating from L3 and L4. You get this degeneration. But where are the other degenerations? There are
contained in the infinite sums.
They're contained in the limit L goes to infinity with some values of theta, I think. And they're hidden in some nasty way. So
the automatic, it's in the OP associativity kind of sense.
Well, it's a theorem that you get all M04, but I think the challenge is imagining in what part of the domain of integration the other degeneration. So what do you have to do with theta and L such that L1 and the puncture 1 and 3, for example, come close together? It corresponds to this curve, the horizontal curve that I haven't drawn here, going to 0. But that's not manifest there. So it must be L going to infinity and maybe keeping theta equal to 0, or at some end.
I would have thought that you can produce the other channels even for fixed L, for any L.
For fixed L, no, you're never approaching the generation.
Doesn't it come from the infinite sums?
Sorry, Dimitri. So we are a bit over time, so I just want to check if other people have questions before we close the session today. So are there any other questions for Barton?
Maybe I just wanted to check one thing, which is that this infinite copies, is it coming because you can take one of the Z's and rotate around the others? I mean, that's a trivial infinite copy, right?
Right. Yeah.
So is that the origin of the infinite copy of M04 that you're getting in the Teichmuller space?
I think so. This corresponds, let me see, this theta going to infinity is kind of rotating, keeping, I feel it's something like rotating 2 around 2.
Yeah, yeah.
And that's infinitely many copies. It's doing that. What is less, you see, so that's a theorem of Teichmuller space. The full Teichmuller space is generated by a single graph. You don't have to sum over different graphs. That's another reason why Teichmuller space doesn't kind of fit. And there's no STU. One channel gives the whole thing, a little like in old-fashioned string theory, which is nice, I guess. But I think the degenerations are terrible. Anderson, this guy cited, this mathematician, was telling me that even this finding the degenerations here is a little non-trivial. And I don't know where, for example, how do you get L1 and L3 to come together? I'm not sure exactly how you're supposed to do it. The one thing that is, you see, maybe there's a little bit of an intuition here. This diagram, I'm going to say something, I don't know how intuitive it is, or but it does give you an idea. This diagram here, if you fix the L's that you can fix, L1, L2, L3, L4, to have, so I think I have a partial answer to it. You fix L1, L2, L3, L4 to have the same length. Now, as L goes to infinity, this area of this diagram is fixed just by topology. So this area is something like 6 pi or 8 pi or something like that. So by the time L goes to infinity, the boundaries L1, L2, L3, L4 are coming together to each other. They're in here, they're moving towards each other because the area has to be kept the same, but the ribbon of this kind of intermediate geodesic is very long. So these circles are going to start approaching here. So at some particular angle, you're going to have the thing happening, and this ribbon is going to become very small because the area is finite. So I think it's clear that somehow you can get the other degenerations that way, because the area is constant. So it's going to fix these things to be kind of on top of each other. This diagram is going to become a little like a light cone diagram looking. Overlaps because of this thing. So it's pretty intricate, but it's remarkable that one single graph in one single configuration of pans, you don't have to sum over all, like in finals, one produces all of Teichmuller space.
So, are there any more urgent questions for today? So if not, I think we can close the session today. So I remind that tomorrow the Zoom room will be open already at 7 a.m. in US time. So you can come anytime you want to discuss or ask more questions if people are around. And then the lecture will start again at 8 a.m. tomorrow, Boston time. Then for your time zone, you can check on the website and set the time zone. Thanks a lot to Barton and Olaf for the great lectures today.
Thank you, Harold. Thanks very much.
See you all tomorrow, and on Zwiebach in between for those who want. Thanks.
Thanks to you.